Hello, welcome back to CoNGA 2022. I'm your host and general chair, John Gustafson. We have two sessions between now and the break that occurs in the afternoon in Singapore. And our next speaker is quite unusual in that he's actually physically in Singapore. So he gets to do this and even see audience reactions, I hope. I do want to remind people that they can go to Pigeonhole and there's a QR code that they can use there if you really want to quickly get into Pigeonhole and easily, or just go to pigeonhole.at and use the passcode SCA22. Please you can submit your questions at any time during the talk. We can see them pop up, but we will save the questions to the last 5 or 10 minutes of the talk after our speaker has spoken. So our next speaker is Raul Murillo. He got his BSc degree in computer science and a BSc degree in mathematics in 2019 from the Complutense University of Madrid, UCM, where he also received his MSc degree in computer science in 2021. Currently, he's pursuing a PhD in computer engineering at UCM. His main research areas include computer arithmetic, computer architecture, approximate computing, and deep neural networks. And I really appreciated the paper that he submitted to this conference, because it was 5 years ago that Isaac Yonemoto showed how to write a very simple multiplier, a VHDL circuit, based on the fact that 2's complement arithmetic is the basis for the Posit representation. But after that, there were 5 years of people who could only think about taking apart the sign, the exponent, and the fraction and treating it with the same kind of methods that had been developed for floating point over the decades. Finally, we got a really holistic and efficient way to do the hardware as Raul Murillo got it. So I'm very much looking forward to hearing what he has to say. Raul?
Can you hear me? Yeah. Okay.
Yes.
Thank you, John, for the introduction. Really appreciate it. Yeah, as you have told me, I'm a PhD student at Complutense University of Madrid, and the topic I'm gonna discuss today, well, it was very interesting for us because we realized that the things that were as Posit were decoding so far weren't the optimal way as they were thinking in the beginning. So we wanted to evaluate them, and the results I'll show you. They are quite interesting. So I will start with some introduction of the Posit arithmetic and its main properties, to then understand how the main components on our implementation are then described. Then I will explain the main different decoding approaches that have been proposed so far in literature. And with this, I will explain the differences in the design of the functional units when implementing hardware. Then we will go with the hardware evaluation of those units, which is probably the main contribution of this work. And then I will shed some light on the conclusions of this work, okay? So, first of all, what is Posit arithmetic? Well, most of the presence here will know, but it was designed, as John said, 5 years ago, to be as an alternative format to standard IEEE for floating point numbers. And this Posit format is usually defined using 2 parameters. The first, the n here we see in this picture, indicates the total bit width of the posits, and the second one is this ES, which is the exponent size, that is the total number of bits that are reserved for the exponent field. So the Posit format usually consists of 4 fields. The first one, it consists on a sign bit, and in a similar manner as integers or floating point numbers do. But then we have a variable size regime, which is completely new, and this one encodes a scaling factor, as we will see next. Next, we have the exponent field, which has many bits as given by this parameter, and the remaining bits encode a fraction in a similar manner as floating point numbers do. The interesting thing here is this new form, this new field, which has variable length, the regime, and this has many interesting properties, but also some difficulties when designing hardware circuitry for this number format. So let me explain some of the main properties of this arithmetic format, which are interesting and will help us to explain or to understand how the arithmetic of the how the hardware data path for this arithmetic format are designed. Okay, so first of all, it must be noted that this format does not use a lot of bit patterns to represent exceptions as standard floating point numbers do. This format, Posit, only has two exception values that are encoded with all the remaining bits except the sign bit equals to 0. Those are for a single 0 pattern. So in this case, there's no negative 0, and also for not a real exception value. Also, it is noteworthy that posits provide, under the same bit width as standard floating point numbers, they provide either larger dynamic range or a higher precision, as can be seen in this plot, in which the values near to 0 value of exponent, that is next to 1 or -1 when dealing with negative numbers, they provide higher precision in this area that is shown as gold in this picture. Also, an important property that is not explored in this work, but is also noteworthy to mention, is that the standard of Posit arithmetic includes fused operations. And it is very important to perform large calculations, like, for example, linear algebra, that can accumulate larger results without intermediate roundings in a register called quad. And finally, as we can see in this ring plot, there is the main idea of how posits were designed. That is that they were designed from a mapping of two complement numbers into the real projected line, as we can see here. And this has very interesting properties. For example, when performing comparison, this can be done in a same manner as integer numbers. So no extra circuitry has to be added for this kind of operations. And this also gives us certain intuition on how this format was initially designed, so we can better understand the different decoding approaches, as I will explain now. As I told before, this format consists of 4 different fields. And in literature, it has been usually used a sign magnitude approach for decoding Posit numbers. This approach, which is similar as the one that is used in standard floating point arithmetic, consists of multiplying by -1 the value of the Posit when this is negative. As we can see from this equation, all the values of the Posit should be extracted from the absolute value of the Posit. And this is very important because for negative posits, we have to perform 2's complement to get the absolute value of the exponent and the significant. Okay. Also, it's important to mention that in Posit arithmetic, the significant has always the value 1 for the integer part of this significant, which when implementing this in hardware can be represented using one single hidden bit. As I told already, this is the approach that has been used mostly in literature, because it's very easy to translate posits to floating point in this manner, and this can allow to reuse some of the circuitry designed so far. However, as we will see along this presentation, this is not the optimal way of proceeding with Posit arithmetic, because they were designed with this 2's complement idea. So there's another approach that is also called 2's complement scheme for decoding posits, that treats negative and positive Posit values simultaneously. So as we can see in this second equation, there is no -1 term that multiplies the value when dealing with negative posits. But the sign bit might change the value of the exponent or the significand on runtime for negative values. For example, if we look at the significant part of this second equation, we can see that when the sign is 0, we have the same significand as in the case before. That is 1 for the integer part, and then we add the fraction. But in the case of negative posits, this equation evaluates up to -2 plus the fraction, which yields to having a negative value in the integer part of the significand. And when implementing this in hardware, this will be translated into having 2 bits or 2 hidden bits for this integer part. And this can be seen like a more complex design, but as we will see later, even the design can be different or more difficult in the beginning. This has very with this approach we will reach reductions in terms of our requirements of the units. Okay. So as we can see from these two equations, it is not difficult to see that in the case of positive values, that is when the sign bit is equal to 0, both equations evaluate the same. But more attention needs to be deserved when the sign bit is 1, when we are dealing with negative values. However, in our work, we proved that both expressions are equivalent for all the positive bit strings. So this is very important because from the analytic point of view, we are dealing with equivalence expressions. But it remains an important question is how this translates into hardware implementation. What is the performance of each decoding approach? And this is the question that we are focusing to answer in the remainder of the presentation. So now I've explained the main different decoding approaches, and now let us see how this realizes or how this translates into the differences in the design of POSIT functional units. Okay. As a short summary for this section, let us mention that POSITs were designed to be hardware-friendly. That means to have similar circuitry as floating point arithmetics, but even simpler, since this format has to deal with less special cases. Remember that we have only 0 and just one value for not a real number. So this can simplify kind of the data path. In this scheme, we can see the general flow when performing operations in hardware for POSIT arithmetic. As we can see, at the first step, the operands can be 1 or can be 2 or can be more operands, but they must be decoded into the different fields that we saw before. And then, with those fields, we can perform the proper arithmetic operation. Finally, the result must be rounded and encoded into a new POSIT of a certain bit width. However, it's important to mention that in contrast with floating point arithmetic, in this case in POSITs, we have runtime variant fields, which might complicate mainly the decoding and encoding stages, as we will see below, because this regime field needs to deserves special attention, okay, as we will see below. So I'm going to explain the first module that we can see here, the decoder and then the encoder, and then we will focus on the main arithmetic operations, which are addition and multiplication. So suppose this is the scheme for the decoder module when dealing with this sign magnitude scheme for decoding posits. If we remember from the previous slides, this kind of scheme requires to have the posit in the absolute value to deal with the different fields. So the first step here would be to take this absolute value in the case the sign is 1. So for negative posits, we are translated and taking 2's complement to have the positive values for the next fields. Next, we can extract the regime by counting the leading zeros or ones. And once we have the regime and shifted the posit, we can also extract the exponent and the fraction fields. And also note how easily in posit arithmetic is to detect special cases with just comparing if with 0 or performing an OR reduce of the n-1 remaining bits. This is the scheme, as I told, for the general decoder module in the case of sign magnitude format decoding. Which are the differences with the 2's complement decoding scheme? Well, as we can see here, in this case, it's not necessary to perform any absolute value or 2's complement because we can deal with positive and negative values simultaneously. And just a little bit of logic for adjusting the regime and the exponent is necessary. Okay? So we are removing some part of the logic which will have some kind of impact on the hardware requirements, and we will see later. Next, let's go with the encoder module. So suppose we have already performed the operation and we have the different fields of the posit encoded, plus maybe some flags for the proper rounding. Okay? In this case, this scheme corresponds to the sign magnitude approach. So at the first step, we will need to extract the regime, that is the amount of bits that should be shifted from the exponent and the fraction, and then perform proper rounding. And in a similar manner as we did in the decoder module, it's necessary to take 2's complement when dealing with negative numbers. So that's the last module at the end, and of course we can easily compute special cases with, in this case, a Mox operator. But when dealing with sign 2's complement decoding scheme, obviously this 2's complement module disappears completely. Okay, and again, some small logic is needed to be added in this case for proper computing of the scaling factor of the regime, right? So now let us focus on the main arithmetic operation of addition. In this diagram that shows this process for sign magnitude decoding approach, suppose we have 2 operands that are decoded with the previous scheme, and at the end we have an encoding module again. For performing addition, we have to compare the operands and detect which is the biggest one. So we can swap either the fraction and the scaling factors, which is the regime and the exponent gathered together. And once we have once we have detected the larger field, we can then align the fraction accordingly to the difference of these scaling factors, as we can see here. Also, we need some kind of extra logic that deals with the sign of both operands, plus the information about which of the operands is larger to perform proper addition or subtraction. And with this result of the addition of the significants, we can finally normalize the results and adjust the scaling factor before performing the encoding. However, all this kind of sign logic disappears when we are dealing with 2's complement approach for the content deposit. Why? Because the result or the sign of the result is implicit in the operation of the addition of the significants. Okay, as we are dealing with significants that have the sign of the original input implicit, then performing addition gives us the sign directly. So no extra logic for the sign is needed in this case. Also, we are eliminating the needed subtractor that we had in the left scheme, and this is because handling the sign implicitly in the significant yields to directly a negative result in case it is obtained by just performing addition. Okay, and finally, it must be noted that the comparator module can be reduced in a couple of bits, because it's only necessary to compare the scaling factors and not the whole bit width of the Posit numbers. Okay, so in this case, again, we are reducing most of the logic of this circuitry. And finally, we have the multiplier module. In this case, multiplication is much straightforward. Just we need to multiply the significants and add together the scaling factors. And the sign of the result is just performing an XOR operation. However, when dealing with 2's complement notation, this logic for the sign is again removed, because the sign is again implicit in the result of the multiplication. But at this point, it must be noted that the inputs for this multiplier unit are 1 bit longer. So this multiplier will be larger. And also, it happens that in the case we have -2 for the significant in both operands, then this multiplicand operation will result into 4. And 4 is not representable in this format, but neither is 2. So in that case, we need to add 2 carry bits to the addition of the scaling factors, which might increase the overhead of this unit, as we will see later. So now we have explained the differences between the functional units when using one approach or the other. Let's show how this evaluates in hardware. How is the impact of using one or another scheme? So for this, we perform self-synthesis using Synopsys Design Compiler, and we focused on two different experiments. First, we wanted to compare or to evaluate each of the individual components presented before, and we targeted the 32-bit precision in Posit arithmetic. And then we wanted to evaluate the whole data path for addition and multiplication. And for that case, we also took some designs from state of the art. 2 of them that are based in this classical or similar to floating point sign magnitude decoding approach, and a third one that is based on 2's complement decoding. However, this third one, Marto, uses a custom format similar to floating point, which they call Posit intermediate format. So we wanted to implement a solution that is full based on Posit arithmetic. So in this case, we implemented our own solution. So finally, we have two designs for each decoding scheme we can compare with. But first, let's go with a comparison of the individual components. In this case, we can see synthesis results for just the decoder module. As we can see, using 2's complement approach reduces our resources in all the aspects when comparing with size magnitude, because we were removing most of the logic regarding 2's complement or taking to absolute value, and just needed to add a little bit of extra logic gates. And we get here savings up to 77% in terms of energy, which is a lot. At this point, we also wonder which is the comparison with standard floating point, because maybe we are gaining a lot, maybe not. Well, we check it for the same module or the corresponding module in the case of standard floating point arithmetic, which corresponds to detecting exceptions and subnormal numbers, plus extracting the exponent and the fraction in the case of floating point arithmetic, which can be done in parallel because it doesn't need to extract the variable size regime, and for that reason the results show much less resources. This is just for having a comparison point, but it's not the point of this work. But it was quite interesting to compare with the other arithmetic format. Also, similar results are obtained in the case of the encoder module, but in this case less reduction is obtained. But anyway, to complement the coding provides, as can be seen here, better our resources. And again, comparison with a standard floating point gives us that posits are still far away from competing with standard floating point. But at this point, it must be noted that the point of posit arithmetic is not to compete directly with floating point numbers, but as they provide higher accuracy under the same bit width, maybe we can use lower bit width to remain higher accuracy terms. So this plot could be compensated in that way. Okay. Next, we have some results of the other code, and this is just for the main logic of the addition without the decoder and the encoder modules. Okay. As we can see, again, removing some of the logic, as we saw before, gives us reductions in terms of area, power, energy, and mainly delay of this arithmetic format. However, this is not the trend that is followed in the case of the multiplication, and this is because of the point I mentioned before. Increasing the size of the multiplier deals to an increase in terms of area and power. However, it must be noted that the overhead here is not higher than 10%, and also this overhead can be compensated with the savings that are obtained in the decoder and encoder modules, as we will see later. So let's go with the comparison with the different modules, the full modules from state of the art. Here we have two designs that are based on sign magnitude approach, which are Pacogen and Flow-Posit, and the other two, which are Marto and Proposit, are based on the 2's complement approach. Also, we perform synthesis for different configurations or precisions for posit numbers, but the major reductions results were obtained for the 32-bit format. Also, as we can see here, from the ones that are based on sign magnitude, Flow-Posit presents a better results, mainly in terms of area and energy. So we compare this with the red one, which is the one we propose in this work, that also provides better results when comparing the designs based on 2's complement format decoding. As we can see here, using this decoding scheme provides a high resource reduction, mainly in terms of area and energy, and also similar reductions, but as mentioned before, with less impact are obtained in the case of multiplication. As we can see here, using 2's complement decoding scheme, which had a higher cost just for the multiplier core, doesn't produce higher cost for the whole multiplication data path, since in this case we have 2 decoders plus 1 encoder that are much more efficient using this 2's complement encoding scheme. So the result is clearly a win for this 2's complement format. So let me finish with some of the conclusions of this work. We saw that clearly posits were designed to be decoded with this 2's complement format, because the results are clear. They provide much less hardware resources, much more efficient designs. But it must be noted that this 2's complement approach deals with or deserves special attention, because the hidden bit or the integer bit of the significand can have different values. Can be 1 for positive values, or can be -2 for negative posits, and this can yield to more difficult designs, or some of the circuits should be redesigned. However, the results are clear, and even it needs some redesign, the designs are much more efficient. And finally, we saw that in our units that do not provide a float to posit conversion, but are just posit circuitry, they are native posit circuitry, they provided better results, improving the state of the art. So we are happy to see these results, of course. I guess here concludes the presentation. So thank you very much for your time and your attention.
Thank you, Raul. Yes, I hear real audience reactions finally. So I have several questions about this fine piece of work you've done, and thank you again for doing it. When you're comparing with the IEEE circuitry, do those IEEE circuits support all 5 rounding modes, or just one of them?
No. The units that are shown in this in the previous plots are basic units that just detect the special cases, the exceptions, and the subnormal cases, and at the beginning and at the rounding of the results. But they are not using multiple rounding schemes, and it deserves more attention, and we plan to extend that for the future work, because dealing with all the possible cases and the subnormal numbers that IEEE have is much more expensive. We expect that,
yes.
But also requires much more logic design. So
yes.
It was not easy to include that in the work. I mean, we expect that results might be compensated in that way, but they were not included in this work.
It is very difficult to find a public domain IEEE hardware definition that actually supports subnormal numbers. They're all leaving it out and not telling people that they're leaving it out. And it actually increases the cost of the IEEE circuitry by about 30%. And all those energy numbers, the power numbers, the latency numbers, they go up significantly because as soon as you have subnormals, they too have to do a count leading zero as part of the decoding process. For every single input, they have to check for the possibility of a subnormal. When you do your count leading zeros, are you using one of these divide and conquer circuits that makes it logarithmic time, or are you actually going linearly?
Actually, we are in these implementations we are using open source FlowPoco generator, which includes some kind of built-in units. For example, this leading 1, 0 counter, and they provide logarithmic times. But
Okay, good.
But the implementation is open source, and we are dealing on that component. Maybe
Yes.
it can be improved for further works, but to have a general data path, that was sufficient for us.
I also noticed when you decode for the multiplier, you're going to have more bits of significance in the posit. You have up to 28 bits of significance, whereas you only have 24 bits of significance for the float. Does that account for any of the difference in the higher cost of a posit multiplication?
Yeah, of course. In that case, you are dealing with more bits, and it has an impact, of course. But just an impact of on hardware consumption, as most of all the bits are necessary for remaining precision in that case. Maybe there can be an algorithm that uses lower bits, but at this point we don't know them.
I'm not saying you should get rid of it. I'm just saying people should understand that you don't get higher accuracy for nothing.
Oh,
if you need if you need more bits and you want to multiply them, you're going to have a slightly bigger multiplier, and that's going to take up more chip area and take a slightly larger amount of power and delay and so on.
Of course.
Than a float.
Well, what Posit has is an implicit format that once decoded, they have more bits. But that's, as you said, that's what gives us more accuracy, and that's not for nothing. But well, our results, accuracy results, and also implementation results showed is that, for example, Posit 32 bits provides a nice trade-off between single precision floating point and double precision floating point, like having the best of both worlds.
Yes. Now, you didn't look at the choir for the cost of the choir, did you?
No, for the work we didn't focus on that, but we have previous works in which we focus on the choir, but as the accuracy was not the point of this work, we let it as a future work and just focus on how can this be decoded and how is the efficient of that. Of course, if we apply the same schema in the case of a choir, we could have hardware improvements in that terms.
I think you should maybe now be able to describe a floating point unit versus a posit unit that has plus, times, compare, and maybe a few other operations built into it, and then you'll know what is the overall savings, because you will have all the pieces and parts that you would use to build a real number processing unit, and you know, you get the advantage of not having the comparison operations, as you mentioned, but then you have the higher cost of having to do some of these other things, and maybe that would possibly even the score a little bit between IEEE and posits. Posits are 5 years old, and floating point arithmetic is about 100 years old. So I think we should allow a little more time for us to find all the good tricks for how do we make these run fast. One researcher I know proposed that you could actually, as you're counting the leading zeros, you could do it with a linear algorithm if you populate the multiplier partial products at the same time. It is possible that those two operations could overlap one another. So by the time you know where the final bit is of the regime, your partial products are already loaded and ready to be added. And that would really reduce the latency and allow you some more parallelism. So I think the single biggest disadvantage of posits is that you first have to decode the regime before you can take apart the exponent and take apart the the fraction. Whereas with floats, you can immediately dive in and grab all those parcels out and then start doing something with them.
Yeah.
If you ignore the subnormal numbers, which everybody's doing these days, saying, oh, we'll handle that with a software trap, which
Exactly.
is cheating.
That is the
Yeah.
same conclusion as we reached with our work. It would be possible to detect the regime faster or earlier, or if it had a fixed length, then we could do much more
Yes.
with the same precision.
Yes, we have, people don't notice it, but half of all posits have only 2 regime bits. The ones that are, you know, between like 1/16 and 16, I think, or in magnitude, all of those have just two regime bits, and you can immediately start decoding the exponent and the fraction if you make that guess. So if we were to apply the same trick that the float people do and say everything else is an exception, you could throw it to an exception handler, but then you'd have 2 different speeds of, some of the numbers would go at a certain speed and other numbers would cause more delay because you actually have to count more leading bits than just the 2. You discover, oh, that was a bad guess. It was a speculation. And I don't know if we can tolerate different speeds for different number inputs, but you didn't look into pipelining any of your stages, did you?
No. We just focused on the main concept of presenting differences in the decoding and encoding. And in this case, we didn't look at the pipeline. All the modules presented here were combinational results.
Yes.
So, but also the ones presented from other papers. So we were comparing all the same under the same conditions, and didn't look further into the pipeline.
Yeah. At some point, there may be some issues of one method is easier to pipeline and another one is hard because it doesn't have a nice dividing point between the, let's say, the decoding step and the arithmetic. I don't know, but that, I think that is an issue to look at in future papers. You've got a lot of interesting papers I think you can write, and it's an impressive piece of work, and I'm really glad you finally laid out the 2's complement aspect of positive arithmetic that's been lying unexploited for all of these years. All right.
Thank you, John.
Thank you again for your presentation.
Welcome.
I think let's move on to let me introduce our next speaker. We're very slightly early, just like 2 minutes early. So I'll maybe give people a little bit of time to sync up. I can practice pronouncing names with an umlaut. Not very good at it. So our next speaker is Moritz Bärthel. He received his BSc and his MSc degrees in electrical engineering and information technology from the University of Bremen in Bremen, Germany, in 2015 and 2018, respectively. Since then, he has been with the Institute of Electrodynamics and Microelectronics, Communication Electronics Work Group, University of Bremen, as a research associate and PhD candidate. His special research interests are innovative digital number formats, digital arithmetic, and hardware implementations of wireless communication systems. Now, for those of you who have been following Unum arithmetic, it went through the first type 1, which as Theo pointed out, is mostly pedagogical, then a more practical type 2 that actually was looking like it might be hardware friendly, except it didn't scale because it required table lookup for things. And finally, type 3, the posit, a lot of posits and valids. But only one group I'm aware of really took the type 2 idea and ran with it and did all kinds of interesting studies showing that by using them to represent sets of real numbers, SORN or SORNs, you could do ultra fast computation on the real, on very flexible sets of real numbers with the disadvantage that it's low precision, and they found places to use that. So I'm glad that they are continuing to pursue that, and I'll let Moritz take it from here. Go ahead.
Thank you very much, John. Hello, everyone. Good morning from Germany. Yeah, and as we've heard, my talk today will be about SORNs and SORN arithmetic. And in particular, I will talk about the implementation of edge detection with SORNs. So as we've already heard, we all know that there are different types of unums, 3 right now, and most of you are, of course, looking at posits. But as we've heard from John just right now, we in our group are focusing on the type 2 unums and the corresponding SORN arithmetic. And by doing so, we are looking into 2 different topics, which are, the first one is the SORN arithmetic itself. So how can we implement SORNs in hardware? What different kinds of implementations we can look at? And the second topic is the applications itself, because even though the type 2 unums and the SORNs are derived from unums, which are universal numbers, so universal by definition, the SORNs are a little bit the special case here, because they have such a low precision. They are not so general purpose than, for example, posits are. But of course, there are applications where we can use them. And that's what we have done in the past. So here you can see 2 examples from our group where we have already investigated the usage of SORNs. One example is from communication. So what we did was spear decoding for MIMO communication system, and there we introduced SORNs as a pre-processing step. And the other example is a machine learning example where we have a support vector machine, and we use the SORNs in order to determine the support vectors for this approach. So 2 examples which we have investigated so far with SORN arithmetic. And today, of course, I would like to talk about another application, which is the edge detection. So from this slide, you can see kind of the actions of me and our group are doing in this topic of SORNs. And at the same time, it will be the kind of the outline of my talk. So I will now go on with the SORN arithmetic itself, introduce the concept and show some insights. And then I will go on with the edge detection itself and show how we implemented it with SORNs, and so show some simulations and hardware results. So you all know this picture. This is the unum circle, the well-known unum circle, using exact values, which we can call the lattice values here, 0, 1, and infinity in this case. And then we have open intervals in between. This is the unum representation. And for those of you familiar with the type 1 unum, you know that the open intervals are in unum representation indicated by the U bit, and the exact values have the 0 U bit, so therefore indicating exact values. But with SORN arithmetic now, we're using a different representation, which is a binary representation of our set of real numbers, which we can see here in the circle. That's where the name comes from, set of real numbers, SORN. So what we do in SORN representation is we take 1 bit for every element of our set, or vocabulary as you want to call it, and we represent each of these elements, so an interval or an exact value, with 1 dedicated bit. So on the bottom here, you can see a very reduced example for a 3-bit data type. Of course, when we implement it, we use larger data types, but this is just for showing the concept. Okay, and from this representation, we then go on to the arithmetic operations, which are implemented with lookup tables, with pre-computed lookup tables. So what you see here is the example for the 3-bit data type and the multiplication operation. And we code all the possible results into this lookup table. So possible evaluations or examples of these calculations could be, for example, when we take the open interval -1 to 0 and 0 to 1, and we multiply them, then we go to our lookup table and look up the result. that's of course how the lookup tables are working. And another example would be for addition, where we don't have the lookup table here right now, but of course that's also possible. And when we take the same inputs, in this case, the result would be the open interval -1 to 1. And this will be then the union of more elements from our SORN representation. So in this case, we'll have 3 elements from our alphabet or from our vocabulary together representing the open interval -1 to 1. So you might think that this representation is very, very low precision, which is true, which is the biggest challenge or the biggest disadvantage of this kind of representation. And even though we go up to higher bits, of course, not only 3 bits, we're still at low precision. So this is the challenge or disadvantage. But of course, there's also an opposite side. There's also a pro, which is the way of hardware implementation, which is very, very small and enables very fast circuits, as we can see here. So this is the example implementing this lookup table, which we see in the middle, with Boolean logic circuits, which only takes very few gates for implementation. And this is what we do. Basically, we take the lookup tables and implement them directly into hardware circuits for using in dedicated applications. Yeah, so that's the basic idea about SORNs and their implementation. And what I also would like to point out is the data types. So we have seen in the previous slide the 8-bit representation, 8-bit when talking about SORN length, of course. So 8-bit means we have 8 elements in our set. So the first data type you see here, the 8-bit data type, is the one we've seen in the previous slide. And this is what we call the original data type or UNIM type 2 based data types, as they follow these representation with exact values or lattice values at the intervals in between. And we can, of course, go to higher bits here. So if we introduce another lattice value, the 2, then we have also the reciprocal 0.5 or 1/2, and of course the negative values and the open intervals in between again. So this leads us to a 16-bit representation. So these are what we call the original data types. However, when implementing this, we've seen that slightly changes to these data types or to these representations can bring advantages in terms of performance. So here's one publication also where we have looked into this data type problem especially. And what we found there was that when we implement the data types or the SORN representation without exact values, we maintain the 0, but except from that, we take out the exact values and go to half open intervals with open boundary towards 0 and a closed boundary towards infinity. So that leads us to a better performance for the applications we've checked so far. And of course, it brings us more dynamic range or more possibilities to play with these data types and insert more intervals or more values. Another thing we have looked up or we have found during this investigation is the spacing or the representation itself can also be implemented differently. So what we have from the original data types is this logarithmic based or spacing between the intervals. So we have 1, 2, and then 1.5. And if we would introduce the next lattice value would be, for example, 4, and then 1/4 on the other way. So this is one way of doing it. This is what we also do with the half open intervals, as you see here, the 15-bit log data type, for example. But another possibility is the linear spaced intervals, which we can, of course, freely choose. So here, these two, which you can see here, the two 15-bit data types, are two examples of these half-open interval data types, and we will use them in the edge detection example within this presentation of this paper. Okay, so that's the basics of SORNs and SORN arithmetic. And now I go on with the application we are looking into today, which is edge detection for image processing. So as a short introduction, what is edge detection? We go from any test image, a grayscale test image. Here we have a picture of a highway. And what the edge detection does is it determines regions in an image or within an image where we have changes or rapid changes between neighbor pixels. And if we find these changes, then these pixels are determined as edges within the paper, within the image. And yeah, so we have a binary image as an output, which shows us certain points where we have these changes in, for example, landscape, or we can define or determine different objects and determine segmentations within the picture and so on. So that's what edge detection is used for in general. And of course, there are different approaches, different algorithms for it. The one we have looked at here is the well-known Sobel operator. And you can see the algorithm here on the left-hand side. So we take our input image, A, which consists of pixel values from 0 to 255. And then we compute gradients in X and Y direction by using a convolution of 3 times 3 matrices. And then we calculate the overall gradient using the hyperpod function. And this gradient then has to fulfill a certain threshold, which is predefined or which can be defined by the user. And if this gradient of the certain pixel fulfills the threshold, then it's set as an edge. And if not, then it's set to 0, so no edge. Here you can see this process of parsing the input image with these 3 times 3 snippets and calculating the gradients per pixel. So that's the algorithm we have investigated. And now I'm going to talk about the implementation. And the first version or implementation I would like to talk about is the reference implementation, because what we did for comparing later on our SORN implementations is we also, of course, implemented a reference implementation in integer values. And it consists of 3 blocks. So we have both convolutions, gx and gy, and then we have the determination of the final gradient. Here in integer, we omit the square root and compute g squared and then compare it to the squared threshold. So that's the implementation of the reference design. All of these implementations, by the way, are done for RTL in VHDL. Yeah, so that's the level we're talking about. Okay, so besides the reference implementation, we've done 2 different SORN implementations. The first one we call hybrid implementation because it consists of an integer part. So the gx and gy convolutions are implemented with integers. Then we have conversion operations for integer to SORN. And then we compute the hyperpod function in SORN arithmetic in order to determine the gradient g. And the third version is a full SORN implementation. So we have the conversion functions to SORN at the very beginning. And then we compute the convolutions gx, gy, and the hyperpod function all in SORN arithmetic. So that's the implementation. And now we are going to look at the performance of the different implementations and compare them. And I'm going to start with the algorithmic performance. And later on, I will talk about the hardware performance or the hardware results. So this picture you've already seen in the previous slide. That's the highway image and the edge result or the Sobel result for the reference integer implementation. And then we have two different results for hybrid SORN implementation and full SORN implementation. In the brackets here for hybrid and full SORN, I stated the data type we used. It's not so important here. The importance is the linear and logarithmic space data types, but the different bit widths are explained in the paper. I will not go into detail here. Just that you know that's different SORN data types, and the number is the bit width, and then linear means we have linear spaced, and log, we'll see later on, means we have log spaced intervals. Yeah, so if we look at these pictures, at first there seems to be no difference. When we take a closer look, of course, there are some differences which we can observe. For example, this car in the middle is detected slightly different, or if we have a look at the border of the road on the right-hand side, there are also differences in the results, but very few one. And in order to have a metric for it, we introduced a metric which we call the normalized absolute error, which basically compares the integer result with the SORN result pixel by pixel, and takes the differences. So where we have different pixels, and this is normalized by the total number of pixels. So this brings us to numbers for this metric. For the hybrid result, which we see here, this leads to 0.018. So in total, a difference of 1.8% between these two pictures. And for the full SORN implementation, it's 2.8%. So this is a number which indicates, okay, the differences are not that high, but it's hard to compare these different implementations or these different results with each other, because we cannot say the hybrid implementation is close to integer and slightly worse, because we can't say integer is better or SORN is better. It's just depending on the application, of course, where we want to use this edge image, or on the threshold we have set, there are differences. So it's not an easy task to tell which is better, which is worse. We can just tell the differences and see that they are nearly equal. So that's what we can see from this evaluation. But of course, one picture is not enough for saying something about the performance of these SORN edge results. So what we did is we used the so-called Berkeley segmentation dataset, which is a set of images, especially for the evaluation of edge detection and segmentation algorithms. And it contains different images for training, for validation, and for test. And for test, there are 200 test images, which we used in an evaluation for our implementation. And the special thing about these data set is that they don't only provide the images, but also so-called ground truth solutions, which are human-made edge results, which can be used for comparison of different edge implementations and the performance of these different algorithms. So I'll show you how this ground truth looks like. So on the left, you can see one of the images from the test set, which is a grayscale image. And then we have the integer edge detection result from our reference implementation. And on the right, you see 3 different of these ground truth solutions, so which are, again, human-made edge results. And as you can see, they have a different level of detail, trying to create an edge result for the given picture. And these ground truth solutions we now use in our evaluation as kind of a third and independent source for comparing our implementation results, not only to an integer reference, but also to this ground truth reference. Yeah, and that's what we did here, and where we can see the results. So as I said, we have 200 test images, and for every test image we have, we used 6 different ground truth solutions, and the metric we used is the one we've seen before, so the normalized absolute error. In this case, we use the difference from the respective edge result, not to the integer reference, but to the ground truth. So each of these 6 ground truths. And this normalized absolute error is then, well, from this error is then we take the mean over all the test images. And that's the value we see here on the top graph. And at first we see the results for 3 different integer versions with different thresholds, all showing a difference between 7 and 10% to the respective ground truth for the first 5 ground truths. For the 6, it's less than 3% or something, I'd say. Okay, but now the interesting part, of course, is comparing this to our SORN implementation. So we start with the hybrid implementation. And here we also evaluated 3 different versions with 3 different data types, all corresponding to thresholds which are at the same level than the integer thresholds. Of course, as we're using SORNs, we don't have exact values at thresholds, but we have to use the SORN intervals at thresholds. So the first thing we can see from this evaluation of the hybrid implementation is that the log-based data type, which is the one with the squares, shows a worse performance than both the others and also the integer reference. So it's up to 15% difference from ground truth, whereas the integer reference with the same threshold is only 7%, roundabout. So obviously the logarithmic space data type performs worse than the others, which are the linear ones. And as we see from the graph, the linear ones, on the other hand, show a better performance with respect to the ground truth solution when compared with the integer results. So we see for the hybrid implementation with 11-bit, for example, which corresponds to a threshold of 255, between 255 and 250. And the corresponding integer reference would be a threshold of 255. And we see that we have a less difference to ground truth. And the same goes for the other linear implementation. Now the same, of course, for the full SORN implementation. And here we can observe similar behavior. So again, the log-based data type performs worse than the others. And in this case, the linear-based data type, which is the 15-bit linear data type we've seen in the very beginning, shows quite an equal performance compared to the integer reference. So this was our attempt of having a performance evaluation on these edge results using the ground truth solutions. Again, I would like to say that it's not an easy task here to say which one is better, which one is worse. That has to be kept in mind. So we can only show differences compared to, for example, ground truth or integer reference. But what is better or what is worse has always to be seen in the context of an application of the actual edge result, which we've not done here. Okay, the next topic is the hardware results, of course, because in the beginning I claimed that we can implement the lookup tables very efficiently with fast and low complex hardware circuits. So what we did is two different synthesis evaluations. The first one for FPGA, which you can find in the paper later on when you're interested. And here I would like to point out the CMOS synthesis, which we did for a 28 nanometer process. And what we see in the table here are the three different versions. So the integer reference design, and then the hybrid SORN design for three different data types, and the full SORN design also for two different data types. And here, all for a target frequency of 1 gigahertz, and also all designs without any pipeline registers, so just the pure circuits compared. And what we see is that all the SORN designs, no matter hybrid or full, no matter the data type, all of them perform better in terms of area utilization and in terms of power consumption compared to the integer result, to the integer design. And we also did a second evaluation, or a second synthesis, where we targeted max frequency. And here we can see that, again, all the SORN implementations achieve a higher frequency than the integer reference, while at the same time still showing lower area and lower power consumption. So this kind of shows what I've said in the beginning. Seems to be that we were right, and SORNs actually are possible to implement with lower complexity, lower power consumption, as we can see here. So, as a conclusion of what we've seen in my talk here, we implemented edge detection algorithms, in particular the Sobel operator, and we implemented 6 different designs, 1 integer reference, 3 different hybrid SORNs, and 2 full SORNs. And from the algorithmic performance, we have seen that at first we achieve a similar performance compared to the reference implementation. We've also seen that the linear-based SORN data types perform better than the logarithmic-based ones. And for the Berkeley set evaluation, we have also seen that the hybrid implementation shows the best performance compared to SORN, full SORN, and also to the reference implementation. And concerning the hardware results, as I've said, for all SORN designs, we achieve lower area, power, and runtime compared to the reference implementation. In particular, these are, so when we come to numbers, we have 47% reduction, or up to 47% reduction in area utilization, and up to 80% in power consumption. So to break it down in a very few words, we implemented SORN versus integer here for the application of Sobel operator, and we have seen that with an equal algorithmic performance, we can achieve better hardware results with the SORNs. That's all I wanted to show you today. So thank you very much.
And thank you, Moritz. A wonderful talk. I had never thought of using SORNs for edge detection before. I've just recently gotten involved with edge detection. I didn't even know that Berkeley had a benchmark reference set that you could use to test them. There is a fellow in India who's building a Posit-based device for edge detection, and he's very interested in your work. I sent him your paper. Maybe there'll be a collaboration in your futures. I had a few questions. First of all, what was the precision of the integer that you used in your integer base case?
We started with 8-bit integers as the values are from 0 to 255, but then went higher when we have the multiplication in the end. So when we calculate the gradient, we have multiplications, and then we go up to a precision of 16-bit.
So in every case, you're using the smallest precision you can get away with.
Yeah,
so you have
right.
trimmed it
So
down.
we start with 8 and then we'll go to
Right.
16 at the end.
No one can accuse you of using 32-bit integers wastefully. You were careful.
No.
Okay. I also noticed, you know how you compute the hypot function of gx2 and gx squared and gy squared, and then you take the square root and compare it with the threshold.
Yeah, in integer.
I think it was slide 6.
Yeah, I'll go back to it if I can.
Yes, right there. Okay, when you detect an edge, if g is greater than a set threshold, wouldn't it make a lot more sense not to take the square root, but to compare against t squared, which you've pre-calculated?
Yeah, that's in fact what we did for the integer reference implementation. So there we didn't implement the hypot, but we just implemented the square and the addition, and then compared to t squared. But
there was no difference for the type 2 for the SORN approach. So you just
that doesn't matter which function we implement.
Mm-hmm. They're all the same cost.
Yeah, if we implement a block which is x plus x squared, or then we take the square root at the end, there's no really a difference.
So did you do the hypot as a kind of a fused operation?
Yeah. Right.
So you got more accuracy that way. You did not get accumulation of rounding error at all.
Mm-hmm. Right. So this is the this is the topic which I didn't cover here, the fused SORNs, but we actually used it here for the hypot already.
Okay, there's a slide in which you show how simple the circuit can be with the AND gate and the OR gate.
Mm-hmm.
There it is. Okay, notice I noticed that one of the OR gates has a very large fan-in, and that's difficult for CMOS to do. There's a limit to the fan-in. You really can't get more than about 3 inputs into a CMOS OR gate, can you?
Yeah, but that's something I guess the synthesis tool you use then takes care of and then splits it off itself. So there's an optimization program running on this afterwards after we implement it.
After the conference, I'd like to connect you with someone who knows how to do extremely high fan-in OR gates at no cost. He's got a very interesting new approach at the lowest level of circuit design. And I think it could change the game for circuits like this in terms of being able to do high fan-in OR gates. Because anytime you do these integer maps of one set of integers to another, you run into the problem of too many bits flooding into the OR gate. Let's see. I guess I was most puzzled by the fact that your hybrid was more accurate than the full SORN, despite having only 11 bits instead of 15 bits. So
yeah,
you used fewer bits and you got better results. I don't understand. You had like a 2% error instead of a 3% error.
Yeah, that is because of the problem, or the main challenge we focus when we have complex data types in SORNs. Complex data paths. So multiple operations followed up by each other. So mainly when we have these blocks with many additions followed up by each other, then we can have the problem that if we do that in full SORN, that we have growing intervals. So we start with just 1 bit in the SORN representation, for example, and as we go through different stages of addition circuits, for example, then for some data the intervals grow, and in the end we have an interval which is too large.
I see. That would also explain why your logarithmic did so poorly. because they spill even more badly than linear.
Yeah, and that's also the main motivation for implementing these fused blocks.
Mm-hmm.
Because then we don't have these growing intervals, because when we do it all together in one block, then of course we can have a higher accuracy in the end.
The value of capital T here, the threshold, did you
Mm-hmm.
tune that up and down so as to get the best possible results? Was that a manual operation of tuning?
Yeah, that's the, you can tune that by yourself as you want. And for everything we've seen here, we tuned it such as we have the best results for every implementation. So for the integer results, we used them. For example, when we compared it to ground truth, we took those with the best thresholds and then compared it to SORN.
Okay, I was just trying to understand the rules of the benchmark, whether you get to hand tune T for every single image, or you set the capital T and it applies to all 200 images.
It's a quite huge degree of freedom, this threshold. So you can do basically so many different things with edge detection when you have a very low T or very high T. So many different possibilities here.
You showed examples of road scenes, and of course, we all think of self-driving vehicles. Am I right in thinking that this is one of the core challenges of self-driving vehicles, is to recognize edges?
Yeah, so that's where the motivation came from, to take this picture, for example. So in self-driving cars, you have a camera monitoring the road, and then from the pictures, you take the edge detection for every single picture, and then you try to put lines into this picture to tell the car where is the road, where are the lanes, for example. For road lane detection, that's the first one, but of course also for then determining other objects like cars. So self-driving cars, self-driving vehicles is one of the main applications of edge detection, of course. But there are many others, like fingerprint, for example, where you also use it.
Yeah, so at some universities I've worked at, they would insist that you patent this and try to make some money on it. Have you talked to any car companies?
Not yet.
And you're not being pressured to?
No, I haven't heard anything yet. But it's
Okay.
it's kind of an early stage, I think, of this work with edge detection and SORN combination.
Yeah, I've seen a number of things come up value where you can make something that much faster, that much smaller, that much lower power. There's almost immediate commercial application for it. And you might want to think about protecting it. If it looks like it's worth real money.
The problem that might come with it, of course, is that you have to implement it either in an FPGA or make an ASIC from it. You cannot just use a general purpose processor or something for it.
Yes, of course. I understand. Well, let's see. What time is it? Okay. We are actually 7 minutes early, but even more than that, we have a gap in our schedule because I tried to line up the breaks with the rest of SC Asia. I was told that we would have this big break from 3:30 until 3:50. So I think we are done now with this part of the session, and we will reconvene at 3:50, if I understand the schedule correctly. We were not able to squeeze in one more talk. I wanted to make sure everybody had at least 45 minutes. But thank you very much for your presentation.
Thank you.
Appreciate it. We'll be back at 3:50. Welcome back to CoNGA 2022. We have 2 submitted talks and 1 industry invited talk that will take us to the end of the session today. The first talk is by Federico Rossi. He's a PhD student of the Information Engineering Department at the University of Pisa. And I have to mention that Pisa is a very special place in my heart because it is the origin of modern arithmetic. Leonardo of Pisa introduced Hindu-Arabic numerals to Europe. and taught everyone how to do arithmetic at like 1500 something. And it was quite the revolution. You know him better as Fibonacci. That was a pivotal moment. So now they're still working intensively on arithmetic, but there's a group that really focuses on posits there. Federico is, in 2019 received his master's degree in computer engineering, magna cum laude. He is currently involved in the European Processor Initiative project, which is also true for our next speaker. His research topics involve alternative real number representations and their applications to deep neural networks for the automotive environment. We have more than one paper in this conference on deep neural networks, but he'll get the chance to give us the first one. So Federico, it's all yours.
Thank you, John, for the introduction. So hello, everyone. Today I will talk about our recent work on a summary and comparison of small real representations for the deployment of deep learning models on edge devices. Okay, oh, too much. Okay, so why we need small reals on edge devices? Just to start, typically edge devices have some hardware limitations, like limited non-volatile storage, limited volatile memory, and limited computational power. These three constraints may limit our possibilities when using traditional neural network models with traditional arithmetic representation that can be IEEE 32B floats or doubles. The efforts we see in the state of art towards deploying DNNs on edge devices are, we saw two main threads. One is focused on the inference only phase. So we want to use edge devices only for the inference part of neural networks, so just for recognition or detection, not for the training part or the labeling part. And here we want to employ reduced precision representations for the parameters of deep neural networks. For example, it's the weights we employ in these networks. Another thread also includes the training phase. Well, we use low precision formats even during the training phase, so even in the training algorithm. These low precision numerical formats are typically alternative representations that we can use to encode and typically also compress, because we use less bits than the original and standard representations. We use them to encode weights, activations, and also, if we employ them in the training phase, gradients. We can see three main categories that we can divide these numerical formats in. We can have low precision floating point like formats, low precision fixed point like formats that can be also integer numbers, and then extremely quantized formats like binary or ternary formats. The low precision floating points are the most similar to the original IEEE 32B float, because they just take the standard format of sine, exponent, and mantissa, and they reduce or modify the number of bits in each field. For example, we have the IBM deep learning float that only has 5 bits for the exponent, 1 bit for the sine, and the rest of the bit for the mantissa. Or the Google bfloat 16 that is very common nowadays as an alternative of the 32-bit standard float that only employs 8 bits for the mantissa, that is the same as the 32-bit standard float, but reduces the mantissa bits. So it is very, very similar to the original one, but with less decimal accuracy. Another approach that we can take to low precision representation is the small fixed point or integral numbers. We can have these formats even in microcontrollers that does not have FPU, The computation can happen entirely on the arithmetic logic units, so there is no need for big processing units that also have floating point units. The computing time on integer numbers is more bounded and predictable than the one of floating point numbers. Integer numbers are typically without special cases, without subnormals, or without any added logic to control special numbers. The training that we can also apply training with these numbers, but it is not straightforward because we need to modify the training algorithm to take into account that we are using integer number. The extremization of this approach is the low precision integers that can be ternary weights or binary weights that have been used by some other works with success to extremely reduce the footprint of models while maintaining a decent accuracy when compared to the 32B float counterpart. Even NVIDIA in its GPUs has started to support down to int2, so 2-bit integers numbers for its tensor processors. Moving away from compressing the weights, we can see other techniques of deploying deep neural networks on edge devices by simplifying their architecture. Typically, when we have very high accuracy model, we also need to take into account other metrics like resource utilization and timing performance during inference. A very big network can be hundreds of layer deep, being very accurate on several model recognition benchmarks, but it can take a lot. It can take an amount of space that is very unfeasible for some edge devices. So pruning is aimed also to reduce the amount of parameters that connects the layer between each other. So the algorithm typically try to remove redundant connections between layers. That means setting them to 0 and freezing the weights during the training. So the core idea comes from the work of Jan LeCun on the optimal brain damage metric. This metric measures the importance of a given weight in a neural network. So how much perturbation is generated if we remove that weight from the network. During the training, the training algorithm is edited so that during the training, the low saliency weights are pruned from the network. That means this means, as I said before, that these weights are setting to 0 and are not more involved during not more modified during the training. Along with the network pruning, we can also have network quantization that helps reducing the memory footprint. It is similar to compressing the weights of a network. So, for example, very large networks that deals with common benchmarks like ImageNet can be very large in their memory footprint for the weights. And low power devices can have difficulties and can be limited by their low power and limited storage capacity for these models. The quantization can solve this problem by compressing and reducing the weights of a ternary neural network. For example, the work I cited in the slide reported they were able to reduce the footprint of a network like AlexNet by a factor 35, while maintaining similar accuracy in recognition to the baseline reference. A more drastic approach to quantization is drastic quantization, where we use binary or ternary weights. A model called hybrid neural network model has been developed by the 8 authors of the work I report in Footprint, and consists in a model that has a mix of 32-bit integers and binary layers. Typically, the input, so the first and prediction, so the last layers are on 32 bits, while intermediate layers, such as convolutional, are implemented using binary weights. They report that reached 95% of binary weights inside their quantized model without impacting the accuracy in prediction of this model. Okay. While quantization seems a very interesting approach and very successful approach at reducing the DNN's weight and impact on low-power devices, we also want to take into account continual learning. Continual learning means that the edge devices can continue the training process during the time, so learning continuously and adapting to the external inputs. If we quantize, we introduce a discontinuity between the training word with, for example, 32-bit floats and the inference word with very small integers. So if we apply this quantization, may incur in this discontinuity that needs a change in the learning algorithm. So if we think about different kind of small formats, we need to take also into account that continual learning is crucial. Quantization use very small integral formats for representation. This, for example, breaks continuity if we want to perform fine-tuning, as we said before. When we talk about small reals, small is very generic, but we intend below 16-bit formats. Among the examples we will report in the following slide, we have the IEEE floating point 16, the bfloat family, and the Posit family. In the bfloat family, one of the most common format used nowadays is the 16-bit fixed point format. Sorry, bfloat 16 is a 16-bit fixed format with 8-bit exponent and 7-bit mantissa. This is very similar to the, as in the picture, to the 32-bit floating point. In fact, they share the same bits for the exponent, while the mantissa is reduced by some bits. This implies that the conversion between the two types is just a shift. So if we shift the floating point 32 of a certain amount of bits, we get the bfloat 16 representation and vice versa. So this is very good if we have conversion between the two, since it's just an arithmetic operation. On the other hand, we have a further compressed format that is bfloat 8. It is a 8-bit fixed format with 5-bit exponent and 2-bit mantissa. A particular implementation of this bfloat enables stochastic rounding. Stochastic rounding is just a way to round the number during training according to certain probability. This enables to introduce a perturbation during the training that can reach higher training precision during the process. This is an example of how stochastic rounding works. So let's imagine we have a large floating point on k bits. K can be, for example, 32 in the standard floating point representation. We want to round this number to a smaller format on k first bits. For example, k first equal to 8. We call m first the truncation of m on k first bit, and epsilon a value 2 to the power from minus k. So we get this probability p, and with probability p we round the number x to this value, adding epsilon to the mantissa, or with the opposite probability, we run x to the original one with the truncated mantissa. A kind of different approach is FlexPoint. FlexPoint aim to build tensors with shared exponent, so that the exponent is only represented one time per tensor, and the rest of the bits are all devoted to representing the decimal part of the number. This can highly reduce the overall memory and resource utilization, because we avoid representing the exponent. Moreover, this exponent can be adapted during the training to match the dynamic range of the tensor and the weights that are evolving during the process. Another further approach are logarithmic numbers. This approach stems from the fact that a common problem with floating point numbers is the hardware occupation of the multiplication, division, and division operations. This scheme is called a logarithmic number system, where a number y is not anymore represented as itself, but as 2 to the power of another number. If we apply logarithmic properties, the multiplication of two numbers is the sum of their logarithms, as we can see. So we can only employ addition and subtraction also to perform multiplication and division. However, this approach requires lookup tables to perform exponentiation and logarithm in a fast way. So it also has these drawbacks. Now we talk about of this format, the Posit number that we are more focused on this work. Posit number are a fixed format representation that can be configured in the number of format bits that we call n bits, and the exponent bits that we call s bits. The format typically have at most 4 fields, or 3 if we set es bits to 0. 1 bit sign. We have a field called regime that has variable length, a variable length exponent that can take up to s bits, and a variable length mantissa. The novelty of the format is the regime field that is encoded with a run length approach. So if the length of the regime is the number of subsequent identical bits that are interrupted by a bit of the opposite value. For example, the bit string 1110 has length 3 because is built by 3 1s and 0, and also the opposite 0001. The actual regime value k can be computed depending on the value that is repeated. For example, here we see that 1 is repeated or 0 is repeated. If the value repeated is 0, k is minus L. If 1, k is L minus 1. An interesting aspect of Posit numbers is that when we have small numbers near plus or minus 1, the regime has the smallest length. So we are reserving more space for the mantissa, increasing decimal accuracy. This property matches perfectly with the range of weights we typically encounter in neural networks. This means that we are not wasting too much bits for the exponential part of the Posit, but we are using them for the decimal accuracy part. Furthermore, a Posit with 0 exponent bits can have has properties that can speed up the computation of arithmetic operators and other analytic functions. For example, we can approximate directly on the Posit representation the double and the half operators. But furthermore, more important is that we can implement fast activation functions with 0-bit exponent posits without decoding them, so just acting on their integer representation with arithmetic and logic operation. For example, sigmoid operation is the building block for the other ones. We start from this, and then we can use other decoding-free operators like true dot, or 1 minus, or the negation, to build other activation functions like the hyperbolic tangent or the extended linear unit. All three of these can be computed, as I said before, without decoding the Posit itself, so just on the representation. Another work that has from other authors is a variant of Posit numbers. It is called adaptive posits. When we convert, for example, a 32-bit float to a Posit with a lower bit count, we want to control the dynamic range with a certain hyperparameter. The parameter is a bias we add to the regime, and we identify with the name RS. So if RS is equal to 1, the Posit format is identical to a floating point 1. If RS is m bits minus 1, the Posit collapses to a pure Posit number. The authors were able to have a decent accuracy with the 5-bit adaptive Posit, so compressing further the arithmetic. Okay. So coming back to the standard application of Posit, we in PISA developed a library called C++ Posit that is a C++ application of the Posit numbers. We designed this library focusing on the integrability of the type we were defining. So we wanted to have a mean to declare a Posit and use it like a primitive number and a primitive type in C++. For example, just declaring a 8-bit Posit like this. To accomplish this, we extensively use the type traits to integrate the Posit class inside the standard in the C++ std library. And this allowed us to integrate the Posit class with the linear algebra library Eigen. Furthermore, we were able to wrap the class inside a Python wrapper and include it inside the TensorFlow framework, so to provide a more higher interface with the machine learning framework. We also propose some benchmarks to see how the Posit can perform in different deep neural network tasks. We used different sized networks and dataset. For example, the small dataset of MIST and CIFAR10, a quite more complex benchmark called German Traffic Sign Recognition benchmark, and then common and big data sets like ImageNet V2 or Pascal VOC. Tested on, again, on different sized networks like LeNet5, EfficientNet, and SSD 300. So these are the results we obtained with our approach, where we compared 32-bit floats, Posit with 16 bits in different configurations, bfloat 16 and bfloat 8. As we can see, the 16-bit formats managed to to have very similar accuracy compared to the baseline float, 32-bit float. So with half the bits, we managed to stay in a very similar accuracy. Even in much bigger networks and complex datasets like ImageNet-V2, we were able to stay within a decent accuracy region compared to 32-bit floats. Even with 8-bit posits, we were able to stay in a decent accuracy compared to the baseline in small tasks. While in bigger tasks, we struggled to match the dynamic range of these pre-trained networks that were exceeding the Posit one. We also compare the timing results of the emulation of these types on a small device that is a Raspberry Pi 3 model. As we can see, we got some result in the 3 different networks for processing of synthetic images. However, as we can see, when we deal with complex networks with big images, we have a very low frame per second capability of processing. This is due for all the types. This is due to the fact that we are emulating them in software. So we are not exploiting any hardware acceleration in this case. So in this test, 16-bit alternatives show themselves very worth to reproduce 32-bit accuracy on wider format, even in other tasks like object detection. Among the other alternatives on 8-bit, Posit 8 stood up against Bflot 8 in accuracy comparison, because Bflot 8 may need a few runs of fine-tuning to perform better in certain scenarios. However, both formats suffered from the lack of hardware support, as we can see in very slow timing performance when we use bigger networks. As a result, we saw that Bflot and Posit are very promising formats that we can use, that can be used as a replacement of 32-bit floats in inference phase. But this, the use of this format is must be tangled with the proper hardware support, because it's a key factor in their employment in neural networks. So thank you for your attention.
Thank you very much, Federico. Appreciate it. I have a few questions and comments, and I'm looking at the audience questions, and no questions have been posted yet. We have a shy audience. They just don't want to. They don't want to jump in there. But this is interesting to compare against another paper that I think we will hear from tomorrow that also used 8-bit posits and also did tricks with the RS value. The RS, by the way, is not a bias. It's a limit. Regime size is what it stands for. So you can limit the size of the regime, but it still has the same meaning. You do not bias it by an integer. There is a value in biasing the exponent when you're doing neural networks. If you make the peak of the accuracy centered about centered about magnitude 1, you make it centered about magnitude like 1/4 or 1/8 by biasing the exponent by 2 or 3. That seems to be an improvement. And if you combine those two techniques, the exponent bias and the regime size limit, then an 8-bit number we found can actually equal the performance of the 32-bit numbers on the small benchmarks like CIFAR 10 and MNIST. It's a struggle because you really do need a dynamic range. You need a ES value of 2. It does 3 is also okay, but an ES value of 2 sacrifices those nice sigmoid properties that you talked about. But I believe these benchmarks frequently don't use sigmoid, they use the ReLU function. which is just, you know,
Yes,
flat.
they use different.
If it's a ReLU function, then you don't need that critical property about being able to create sigmoid functions with a very quick operation. So I would urge you to try some larger exponent sizes and see if you can actually get more performance out of these low precision, because there's just no way to do a AI without a pretty decent dynamic range of at least eight orders of magnitude, I think, especially on the small side. You don't need it on the high side. You need it on the small side. I also wanted to point out that the IBM DL float is a 6-bit exponent, not a 5-bit exponent. It's IEEE. It's IEEE half precision. The standard 754 has a 5-bit exponent, and everybody finds that that's just not enough for neural networks. You need a 6-bit exponent when you're doing training. I don't know. Anyone else have any comments? We are done quite early. I see that we have our speaker, our next speaker, Benoit, is here. Maybe he has some questions. He heard most of this talk. He can jump in here. He could actually ask the question live.
Yes, it so happens that we had a joint work with Federico in the scope of a European Processor Initiative project. So I will not anticipate my talk, but what we find is that Posit 8 standard of today with the exponent size of 2 is excellent, and I will go into detail. So I concur with the result presented here, but for us, from our point of view, we are very happy with the Posit as they are in the standard.
All right. No more questions or comments? Well, if this was a live conference, we would be able to just accelerate the whole thing and jump to the next talk and give you that much more time. I'm a little bit leery of doing that because I think we were going to try to keep on time. But if you're done a little bit early, and it's as long as the overall session lines up, I think maybe we should move on to our next speaker right away. And give you a head start, and maybe you can take more time if you want it, or if you don't take it, then I'll hand the time to the third speaker. He's already okay. So our next speaker is Benoit Dupont de Denechen. He's the Chief Technology Officer of Calray. He is the main architect of the Calray VLIW core. This is an accelerator. It's deep learning coprocessor, and he's the co-architect of the Calray MPPA many core processors. Before joining Calray, he was at STM Microelectronics and was promoted to STM Microelectronics Fellow in 2008. Earlier, he worked at the Cray Research Park, Minnesota, and directly contributed to the Cray T3E production compilers. Benoit authored 16 patents in the area of computer architecture and published over 60 conference papers, journal articles, and book chapters in the areas of parallel computing, compiler design, and operations research. My recollection is that in the European Processor Initiative, Benoit is the technical lead for the accelerator part of the program. Is that right?
Well, to be more specific, in the first phase of that project, there was a line of HPC accelerator and the autonomous driving accelerator. We did the autonomous driving accelerator. And now there is a second round of this project where it's more focused on the HPC. And so we are doing an alternative. The main accelerator for HPC is based on a vector extension of a RISC-V. And the alternate accelerator is a Calray one. And we'll see competition is good.
Yes. I can't resist pointing out that I noticed the de Denechen last name and thought can't be that common a name in France. And certainly he is the cousin of Florent de Denechen, who also writes so much about positive arithmetic, not always so favorably. So that must be an interesting family conflict when you guys get together.
Exactly.
Fun. Okay, let's take it away, please.
So I will present this work that was done by Oregon, who's going to do a PhD at Calray. Diana Resmerita, who just finished her PhD on a deep learning compression at Calray, and myself, CTO of Calray. So you mentioned the arithmetic lab of Florent, and in fact, he will be the thesis advisor of Oregon. and myself, I will be the Calway representative and work director. So there are academic discussion on what Posit can do or cannot do according to some, but this person will be the joining between the two views and use of Posit. And that's her work mostly in the design part I will present now. So let's try to move. I heard that I'm supposed to have the control of the slide. So I don't know how the slide moves here. Okay. My slide, yes. Okay. Now I will present his work in four main components. And I will have started by a quick recall on what we are doing with regard to deep learning on a many core processor and what would be the use of Posit in that product. So Calway has been starting for more than 10 years now. We are doing many core processor. Currently, we are the third generation of the many core processor. It's a 16 nanometer node. And the early instance were not so much focused on deep learning, and we saw that we had a significant potential there. So we did the first machine, which is a silicon we produced almost 2 years ago. That's the third generation MPPA. It's up to 20 deep learning tops in int 8.32. And we are reiterating this particular processor still in 16 nanometer. And we will do the tape out the third quarter of this year. We hope to have the sample end of this year, early next year. And we will have done significant improvement in the deep learning inference and also part of the arithmetic, including 32-bit floating point. And after this second iteration of the third generation, we will move to the fourth generation MPPA, which means massively parallel processing array kind of architecture, and we will move to a lower technology node, and really will improve significantly again deep learning performance. So we call it a many core processor because the machine is composed of a compute cluster, which are more like compute units or streaming multiprocessor of GPU. So inside the compute cluster, you have a SMP-like machine. In our case, it's based on a real software programmable core. Each core can run Linux, for instance. And those compute cluster or compute unit, we put them together on one or two dies, and that gives us the many core processor. So we call it a many core because you have this cluster level, which is architecturally visible. We have a local cache currency here, and we can also configure the local memory either to scratchpad memory or in a level to cache. Level to cache is shared by the 16 cores. And last, the core, in fact, it's more like a processing element. And it's based on a 6-issue VLIW core with a quite powerful floating point unit. And it has a deep learning coprocessor. And this is where the computation related to deep learning are done. More specifically, this coprocessor, we call it tensor coprocessor. It has a separate register file. So the VLIW core has a 64-bit general purpose registers. But then the coprocessor, it has a 64 256 bits, that is 32 byte register. So it has a much more local storage accessible as register, and the load store interface to the local memory, which is again either configured as scratchpad or level to cache or a partition between the two. Load store bandwidth is 32 bytes, with data going either to the core or to the tensor coprocessor. Now, this tensor coprocessor, in fact, has a load store of 32 bytes, but operate on a bigger operands. The operands are seen as a pair or quadruple of the big register. So you have a 64 byte or 128 bytes, that is 1024 bits of operand which are operated. And this coprocessor is tightly coupled, that is, it receives the instruction stream directly from the main core, and in fact, it's as dedicated to issue lane on the 62 reliable. And there are some interesting features in that. In particular, we don't need to have a convoluted memory layout for the parameter and activation. We manage that we have a load that scatter data into the coprocessor register. So we always operate simple data layout. I will show, even though we have data in memory, the activation are row measure order and the parameter only need to be column measure order. So what is the main operator we use for this deep learning performance? And I will explain why this Posit. So we have int 8 to accumulate to 32 for the quantization in integer 8-bit. And we have FP16 multiply accumulating to FP32 for the floating point support. This removes the need for quantization and the complexity that come with the fake quantization during training. So this is a typical operation we will use and have the Posit data fed into it. So this is our current design. So we take two operands. And two operands, these are matrices of 8 by 8 column by 4 lines of FP16. So it takes 64 bytes. So for it, it's a pair of input, it's a pair of register. The B operand is also a pair of register. It's transposed just before the matrix multiply accumulate. We matrix multiply accumulate, and we obtain a 4 by 4 matrix of FP32. That is again 64 bytes. A pair of a coprocessor register. So the peak performance we get from that is 128 fuse multiply add per clock cycle per processing element, and currently we have 80 cores and tensors, that is 80 processing elements, and this is how we reach this amount of performance, 25 gigaflops, sorry, teraflops. At 1.2 gigahertz. What is exactly the innovation of this operator? In fact, it's a work by our lead computer arithmetic expert, Nicolas Bruni, who published in 2017 how you can, when you use FP16 values, you can expand them completely to fixed point, and then after the multiplication, so you multiply the mantissa, you have 11 bits, you obtain 22 bits, and then you accumulate them, and that gives you, and then you align with the exponent, like Jen mentioned, the exponent range of FP16 is quite limited, it's only 5 bits, so you can expand that to 80 bits, and then you can go into a bigger multi-adder, and you have all your dot products. You have all the products accumulated into a big integer. But us, we need to do dot product of FP16, and we accumulate with an accumulator whose elements are FP32. So we have another path where we expand the FP32 to 128 bits, and then we do the big add. So the key point is that we have this operator. It's very powerful. It can go very deep, and it only does one round of rounding at the end. And in fact, we could eliminate that rounding, like it's mentioned with the prior technique, for instance. But today, for easier integration with the deep learning framework, we do FP16 and multiply and accumulate it to FP32. Now, given that was what we have implemented, and what we will continue, we say, okay, We are not going to change everything for Posit, but we want to leverage the amount of information compression we get from Posit. And that's the motivation for the work. So what use of the Posit can we have in that context? So I recall, but has been discussed in length, what you can do, and that's the domain of arithmetic compression. So we did work on deep learning compression in general, but here we are focusing only on arithmetic compression, that is the change of the representation of the deep learning parameters. You could also, and that we'll discuss maybe later, do arithmetic compression on the activation values themselves. But we started by the deep learning parameters. So what we want is to reduce the model storage memory size by compressing what is originally the FP32 parameters into 16-bit. So we do that in production. It goes very well. And we would like to compress more to 8-bit. So this is why we started investigating the way to arithmetically compress the floating point 32 for the parameter part of the deep learning inference. So we recall it's very well known that we have the FP32. This is the baseline. The binary 16 that we select. We selected the binary 16 because it's also compatible with the other application we do with the processor, especially image processing and some area of signal processing where people are no longer using or deploying very much a fixed point. Now, you all know the bfloat. It's very well known, and we'll see it's very good, but bfloat, you cannot do the full expansion to fixed points that we managed to do with FP16, and it's only good, in fact, for deep learning inference and training. So we didn't select, even though we designed bfloat to see what was the outcome. And then after, for this small floating point, we had a look at Microsoft FP8 that they did for the deep learning infrastructure on FPGA. So it looks like a good idea. You take FP16 and do the same thing they did for going from FP32 to BF16. That is just truncate bits from Mantissa. But then what remains is only 2 bits of Mantissa. It's very small. And of course, we had a look at Posit, and in part of our case, it's Posit 8, because we have FP16, but we want to go beyond FP16 for the compression of deep learning parameters. So this is very well known now, but the key difference is that in Posit, you have 4 components of the representation. And the one that needs some care and the non-standard way to deal with it, and we'll discuss in our implementation, is the regime. So the regime is a string of bits that can go in an array, and you have a terminating bit, which has an opposite sign, or the terminating bit of the regime is out of the range, so it's not included. But we have to deal with the regime, and then when the regime doesn't take all the bits, you get bits for the exponent up to the maximum exponent size, and this is the main parameter we're going to discuss for Posit 8. We look at exponent size maximum of 0, 1, or 2, or 3 bits. And then after, there are fraction bits depending on where we are. So it's apparent that we have a lot of area to adjust the representation of numbers, because first we have the tapered precision with the trade-off between regime bits and fraction bits, and then we can also play with the exponent size parameter, and that's what we're going to do. So first, we want to be sure we are not going to mess up completely the application that we target. So currently, we mostly do inference of classification networks and detection networks. For detection network, for instance, we demonstrated 2 years ago at CS YOLO V3, and we were over 15, and now we are more over 20 FPS in floating point, and that's better than the Xavier from NVIDIA, which is at 18 FPS, for instance. But nevertheless, so we do a lot of classification and detection. So in this particular work, we did the 13 network in classification and one in detection, but we only report the result where they are interesting to discuss. So how we do evaluate the effect of using a smaller floating point representation. In fact, we are compatible with Caffe, TensorFlow, and ONNX or NNX representation in our deep learning compiler. And so we can take any of those models and compile them and generate code for 1, 2, or 3 compute cluster of a machine, because we can decide the inference will run on some or the total part of the target processor. So to do the experimentation of the effect of arithmetic compression, we take the pre-trained models, and it's a TensorFlow typically with FP32 parameters. Then we say for a particular compression mode of the parameters, we do a rounding to still in FP32 of the nearest value. So if we have a posit 8, we convert back its value into FP32, and that would be the new parameters of our deep learning model, and we will run for inference through a standard execution. Can be a machine, can be GPU, can be CPU. But the point is that we have reproduced the effect of changing or of compressing the parameter representation by doing the true representation if it expanded back to FP32. So we did the first round of experiment by doing a uniform compression on all the parameters. And then we observe, and that's my next slide, that it doesn't work so good for some of the operators, also known as layer, in particular, the batch normalization. So we did another round of experiment, not compressing the parameter of batch normalization operator. So we have the results here. So it's accuracy 1. So accuracy 1 means you look at the top class of your network, and you look at if it's at the same as the target label. Top 5 you look at as the 5 highest class of your network, and you look at if the target label is part of those 5. And then this is for classification network. For the detection network, there is another measure, a criterion of quality, which is the mean average precision. So recall the precision is the ratio between the true positive divided by the true positive plus the fake positive. There are other measures like the recall, but we use the mean average precision. Now, we look at for those networks, what happened when we compress the parameters, first of all the network layers, network operators, into different representations. So we see basically FP32s at the baseline, okay, and we have the criterions. FP16 is very good. So for us, at the option, we decide, deep learning compiler, we use FP16 for that operator or not. In particular, it's not by operator. Technically, it's by tensor. We decide each tensor, which is an intermediate value, is going to be compressed or not according to FP16. Keep FP32, do int8 quantization, or do the more advanced floating point compression we discussed now. We see BF16 is excellent, and due to some arithmetic things, I don't understand the details, sometimes it's even better than FP32. Must be an artifact, the way the criterion is represents the reality. Now, if you go to Microsoft FP8, could be called BF8, it's more or less the same. You see it's quite not convincing. So in green is what we assume it's good enough. In orange is not sure if we can accept this amount of degradation. And when we have no color, is that we don't accept the result of compression. This is for the BF16 and Microsoft 8 and Posit. Now we see that on Posit, first Posit with the exponent size of 0 has not much value. So we started with that one because in the early iteration of the POSIT standard, the exponent size of POSIT 8 was 0. So for us, it was a baseline. So we have this one. Now, if you have 1 bit of exponent size or 2 bits, you start to be better. And in some time, even 3 exponent bits are better than the 2 or the 1. But we also see that there are areas, the ResNet, Inception, etc., where we are not fully satisfied with the results. So we found out that it's not, the reason is that because we did compression of all parameters. So it's better in such case to not do the compression of parameter, in particular on the batch normalization operator. And when we do that, it's good news is that we recover a good quality of inference for the networks that didn't respond well to arithmetic compression with POSIT, whatever the exponent size. Now we also observe that for mobile net, whatever we do, even excluding the batch normalization, it's not a satisfactory result. Mobile net has a different way and very shallow separable convolution, if I recall well, so that could be the explanation. But the outcome is that overall, POSIT 1 and POSIT 2 perform very good, better than POSIT with the exponent size 3 in most cases. And I don't discuss POSIT with exponent size 0 because on those experiments, at least, we didn't see a value from it. And it also indicates when we compress a parameter to small size that possibly or very likely there is value in tuning the type of compression, that is, you compress or not, and you use a different exponent size depending on the tensor and not uniformly across the network. So to summarize, we understand again why we observe again why BF16 is so good. We see that FP16 it has drawbacks, but it's more standard. It has more use than BF16. Can benefit for more advanced implementation. That's what we did. And with regard to training, for inference, it's quite okay. For training, I don't know if people are aware, but there are patents by NVIDIA where they explain that you can do the backpropagation with FP16 by having an additional scaling factor that you adapt, so you don't have two small numbers when you do the backpropagation. So in principle, it's also possible to train with FP16, even though now people are more like using BF16 or the new TensorFloat from NVIDIA. For the Microsoft FP8, it just shows that if you take IEEE like that is 3-component binary floating point approach to such small size, it will not work at all. Perhaps it's useful in training, but we didn't do any work in training. Now for the POSIT 8, again, it's a POSIT with the size 1 or 2 of the exponent size, which works well. For the neural network, we did, but again, we did only like 1 or 2 dozen neural networks. We only report 6 of them or 7 of them in the paper. But we don't know what will happen when we start tuning the compression of parameters tensor by tensor. So it's not just say only keep 1 and 2 and that's it. But nevertheless, we see that now this motivates what we do. We will design a hardware decompressor to go from POSIT 8 into FP16, and then that will feed our deep dot product accumulate FP16.32 operators. And that's we have to design now this decompressor. So it's a decompressor because we only do that to the parameter before they feed the multiply accumulator. So our objectives is to take all the exponent size between 0 and 3 and decompress to FP16. And the exponent size for us is not a constant it's a variable input. It's provided by the instruction opcode. You have a two-bit field that is fed from the instruction opcode and then goes into the decompressor hardware. And because we have a load bandwidth in each P of 32 bytes per clock cycle, we need to instantiate this decompressor 32 times. So it has to be compact and it has to have a small leakage and, if possible, a small dynamic power. Because we are fully IEEE compliant, we support all of the rounding modes. So when we do arithmetic computing or deep learning inference, we always respect the rounding mode, and we also have the IEEE flags correctly computed. What we observe is that FP16 has a limited dynamic range, like was mentioned, but being a plain IEEE floating point, they have subnormals. And what we see is that the subnormals are very important, in particular for Posit 8.2, that is with a 2-bit of exponent size, because with underflow, you can represent all the small magnitude Posit 2 numbers. So you need, for the conversion, the decompression between Posit and FP16 to take into account subnormals when you decompress. And so we have a challenge or new things to do compared to the previous work. It's similar to what we did. The previous work is based on decompressing the Posit format into an internal kind of floating point representation, and then operating that floating point, and then going back to the Posit format. But thanks to the Posit, they don't have to deal with the asymmetric representation of numbers. Us, we do have to take into account that we don't have the symmetric distribution of numbers, and this makes our life more complicated than previous work dealing only with Posit arithmetic. So the details is that Posit with exponent size 0 and 1, they all fit perfectly in the range of FP16. There is no rounding, no approximation. For Posit 8.2, it's only 8 value of a large magnitude that we cannot represent at FP16. So we will do overflow or for those guys. But we don't have underflow, because if we have the subnormals in FP16. And for Posit 3, we have 46 values which are beyond the range, either overflow or underflow the representation of FP16. They even cannot be represented in BF16. So now we had an insight, and that was a work by Oregon, the next PhD between the arithmetic lab of Lyon and Calway. And she saw that, in fact, if you want, you can pre-detect overflow and underflow during the conversion very early, just by looking at the regime bits. You don't have to do more processing of analyzing the value carried by the Posit representation. So it's a sketch here. You have more details, and there are details to take care of in the paper. But basically, you look at the combined exponent of the Posit representation. So combined exponent, you have a 2 to the power exponent size by the regime value, and you add the bits of the exponent field of the Posit, and the exponent bits. They represent a positive value between 0 and 2 power exponent size minus 1. And then we compare that to the max exponent and the mean exponent of the FP16 representation. So the max exponent, it's 2 to the power of the width of the exponent, which is 5 bits minus 1, and similar for the mean exponent. But now I'm looking at the conversion part for overflow. So for overflow, you look at the max exponent, and in fact, you can observe that in case where the exponent max of FP16 plus 1 is a multiple of a 2 power exponent size, then you can only, you don't have to consider the exponent field coming from the from the Posit representation. You only have to look to the regime value. And this is possible under those conditions. For FP16, if the exponent size is lower or equal to 3, and for FP32, and also for BF16, if the exponent size is lower or equal than 6. And with that, you know, just by looking at the regime bits, if you're going to overflow. For underflow, it's a similar line. It's more involved because now you have the value of the you are looking at the most negative value of the exponent, and you compare that to exponent mean of the floating point. Exponent mean of the floating point, not only you have the exponent part, but you have to take into account the fact that you can go down because of gradual underflow and subnormals in the IEEE arithmetic. So it's a little bit more details, but the end result is that for FP16, the exponent mean of FP16 is -24, and that's a multiple of 8. And that if we have exponent size lower and equal to 3, then we know that exactly just by looking at the regime, we know if we're going to overflow and underflow. And that's quite helpful in the design of an operator. So the summary then of this insight is that for Posit 8.2, we will overflow the conversion of FP16 if we have the regime value in binary is greater than or equal to 4, else there will be no overflow in the conversion, and we will have no underflow because all the small values become subnormal in FP16. For Posit 8.3, we will overflow if the regime value is greater than or equal to 2, and will underflow if the regime value is lower than or equal to -4. And this is just what we have to test in our implementation. Now, this is the overall view of the operator. I'm checking time. Okay. So it looks complicated, but then we'll zoom in a particular part. So we have the Posit value at the particular exponent size as the main input of 8 bits. And we have the exponent size, like I mentioned. For us, it's not a constant, it's a variable at this point. And then we go into the details. But so the summary of the step is that we first take the 2's complement absolute value of the Posit number. Then we combine we compute what we call the combined exponent. That is, we have the regime contribution and the exponent bit contribution. So we call that C, combined exponent. And then we activate a special case table to output the special case of FP16. It's and we don't deal with the sign because the sign is appended after. So we have the infinite output. We have the largest magnitude output called omega. We have the smallest subnormal number. So it's a binary 1 on the 16-bit, and we have the 0 value. So these are the 4 special cases we have to activate somehow. And then we have another table, which is a subnormal table. So we have to tabulate the subnormal value we want, and that depends on the combined exponent that we will compute. And then we have very early, thanks to the insight we have on the overflow or underflow during conversion, we have the command of the multiplexer at the end. That come only from the regime bits. A little bit more details on this part that computes the combined exponent. So that first construct the combined exponent and then compute the unbiased exponent of FP16. So we have the regime, we extract the regime. So we have a leading digit counter and we shift. And then we know that all the shift we are going to do, it's driven by the exponent size, which is again a variable input in our operator, and the maximum we consider is 3. So all our shifts are measured in 3 minus this exponent size. So we do a leading digit count to find out what is the numerical value of the regime. Then we shift, and then we position the mantissa bit by a first rush shift. Then we do an alignment to prepare for receiving an alignment by left to concatenate the exponent bit of the Posit with the value of the regime which has been put into binary representation. We put with them together, and then we do a last shift right to produce the unbiased FP16 exponent. So what we have is that we have a leading digit count and 3 small shifts, but they are in a series. And so we have a smaller chart that explains what happened to the different parts. But in the paper, we did the four case of exponent size, and you see exactly what the shift means. And so this is our main combinatorial decompressor. And we also have a table implementation. So you can say, well, my posits are not so many, it's posit 8. If I add as input my rounding mode, and in fact, I don't have that much information to tabulate. So I could put everything into a lookup table in hardware. And so we have to compare against this solution. We also see that posits are very symmetric. So we could, in principle, half cut by 2 the size of the table by just abstracting away the sign and working with the absolute value, and then pasting the sign to the end result. But in fact, it's not always possible. But these are the 2 options. We compare our combinatorial design to this table, either plain table or factor table with regard to sign. And sorry, I should have said one thing, is that when we do the combinatorial operator, we have the one cycle version of it, and we have the pipeline version of it. When we do the pipeline version of it, we only add 1 pipe stage between the leading digit counter and the series of small shifters. The experimental comparison is that we use the CAD tools and process design kit we have for production today. So we use Synopsys design compiler, and we have a TSMC 16 nanometer FinFET compact technology node. Our current product works at 1 gigahertz plus. The next silicon we are discussing, we are targeting a normal operating frequency 1.25, and we did the design for what we are looking at, especially the 1.5 gigahertz. And against 16 nanometers. So you can anticipate that it will be quite different when we move to a 5 nanometer on the 4th generation. And now we compare the combinatorial to the lookup table. So the lookup table here, it has, we cannot factor it. And we cannot factor it because when you take into account the rounding mode up and down, in fact, the symmetry of the output is no longer maintained, so the table will not be able to abstract away when you have to when you want to produce result relative to the round up or round down command. So the total input size of the lookup table is 12 bits. You have the 8-bit of posit, the 2-bit of exponent size, and the 2-bit of rounding mode. Now we see that. On the chart, we do 3 charts. We do 1 chart, which is the area in square microns. We do the dynamic energy consumption reported by the CAD tools, and we only take into the account the combinatorial gates. And when we have the pipeline operator, the combinatorial gates plus the flip-flops that do the pipe stage. We eliminate, but that's a standard technique, from the power measurement, the noise taken by the test bench, which are pipe stage before and after the combinatorial operator or the lookup implementation. So when we compare these, we basically observe that combinatorial circuit starts good. These are the square, this is on the left-hand side, these are the square lines. Curve, sorry, but when we start to push the frequencies, and it starts to expand in size. That's a natural result of synthesis. Whereas the pipeline combinatorial implementation is very flat, and anyway, it's better than the table implementation. So this is for the area. For the dynamic power then you see that it starts the same more or less, but again, we have the lowest power is from the pipeline combinatorial, and same observation with leakage. The leakage is in nanowatt. The dynamic power, it should be dynamic energy is in milliwatt. Now, this is the most general implementation. But in fact, you can start to investigate, well, maybe I can remove constraint from my design and see what I get. First, what we thought is that if we want to factor the table, it's too bad the round up and round down prevent us from doing so. And by the way, most of computation we see, particularly in deep learning, it's a round to nearest even. So let's assume that we don't need all the rounding mode. Round to zero, it's mostly used in conversion between integer and floating point. So we want to compute with round to nearest even. So let's focus on that. So when you do that, you have a different effect. So the main combinatorial implementation, we will stay more or less with a simplification by reduction of the special case tables. And the table implementation will now be able to either keep the table implementation as before, but with less input bits, because we remove the rounding mode, the plain table only has 10 input bits. But now if we do factor table with the absolute value, which is the input to the table, and then we paste the sign after a lookup table, then we have only 9 input bits. So now on this curve, you have 4 contenders. We have the combinatorial, we have the pipeline combinatorial, we have the plain table and the factor table. I should mention that when we decide to not consider anymore the round up and round down, it's only those rounding modes, they only affect the result when you are in overflow or underflow mode, because otherwise, when you are in the exact expansion, rounding has no effect. So it's really a marginal, in fact. And so what we see is that, again, we have a very good and very flat result for the pipeline combinatorial implementation. The table is improved, but not that much, going from 12 bits to 10 bits. But now the factor table start to be quite good compared to the plain table. But the factor table is not better than the 2 implementation, except when you push the frequency. But when you push the frequency, the best option is still the pipeline combinatorial implementation. You look at a similar effect for the dynamic power and for the leakage power. So first, we did the first specialization. It looks like a quite reasonable compromise to do. I will only work with the round to nearest 7, and we have those gains. But the combinatorial implementation in pipeline mode is the best. Now we do last specialization is that, well, we saw that we started with all the interesting value of exponent size, but now, and especially a few years ago, the standard Posit was Posit 8 was exponent size 0. So we have this one. But now the standard Posit 8 is exponent size of 2. So it's interesting to see if we don't care about the other exponent size, only focus on exponent size 2, because we show in our experiments, exponent size 2 is always either the best or on par with the exponent size 1. In one case, a slightly better exponent size 3, but it's not that significant. So what happens if we decide now we not only we do round to nearest even only, but also we only do exponent size 2. And so, of course, then the combinatorial operator will be drastically simplified, because all the series of shifters, which are variable input of exponent size, now disappear. And the tables, they get compressed because you have 2 bits of input for the tables that go away. So we are at 8 bits of input for the plain table and 7-bit of input for the factor table. Now we do the experiment again. And what's happened is that pipeline implementation on the area, when you increase the frequency around 1.5 gigahertz, that our operating point, it's still the best. And for the dynamic power and for the leakage power, it's still excellent. So, and it was quite a surprise because we assume that after you go to that simple, the lookup table will win. But on the contrary, if we what we observe is that when we increase the frequency, the combinatorial logic we have in front of the lookup table when we want to compress the input, in fact, start to cause problem with the area and with the power. And that's because the synthesizer has to compress the latency of this particular part, that is taking the absolute value of the number. So if we recap, we see that we have a main operation and we have two specialization. Overall, we reduce by 2/3. We get 2/3 simplification in area and power when we do those two simplification. And so it's interesting, but not so big. So if you have the pipeline combinatorial operator, full generality, and you go down to the most specialized, okay, you can gain, but not a factor of 2, you gain a factor of 0.66. But that's a good result. So now I'm coming to the conclusion, is that Posit 8 was really effective for deep learning parameter compression. It's a good alternative to 8-bit integer quantization because we don't have to do the fake quantization. The fake quantization is where you, during the training process, you change the value of your activation and parameters during the forward and backward passes to introduce feedback about the effect of quantization into your training. So you have to do a fake quantization when you use 8-bit integer quantization. The alternative of a 8-bit fake quantization is to do calibration post-training. But in fact, the post-training calibration, where you do the histogram of activation and then try to find the range of quantization, it could be even simpler with the Posit compression parameter, because we just have to do a calibration with regard to the parameter which are static. We don't have to play again all the data set. So Posit 8, that's our insight, is very good for the compression of deep learning parameters of the classification and detection networks. Now, what was interesting for us was the insight about what happened when you want to convert Posit to FP16. In particular, when you can only have just have to go to the regime to know whether you're going to overflow and underflow. We did a design of this operator in 3 variants, and including the one where it's only standard Posit. And given the what we found in that work, it's motivated us to go beyond, and that's in the future work. Possibly in the 4th generation MPPA processor, we will go for the compression of the activation. The activation are the value you compute the input and output tensors. And for these, currently we operate them in FP32. By compressing them to Posit 8, then we could have a lot of activation memory space compression. And that would help us to have more activation on chip and increase the performance. So the future work will be, can we design FP32 to Posit 8 compression? Thank you.
Thank you. Excellent talk. And I wanted to make a couple of comments about the formation of the standard. It is the one thing I really regret is you make a guess as to what it should be the exponent size. You don't have a wealth of experimental data in the early days of a new standard. And we guessed that 8 bits would have 0, 16 bits would have 1, and so on. And you keep increasing by 1 the number of exponent bits as you doubled the size of the precision of the number. Then we got dozens of articles on how to use posits for neural networks, for inference and for training, and also for signal processing. And they all said exactly the same thing. ES equals 2 is the right size. It's the sweet spot. They get the best results on everything. So now we have the problem that the new standard says ES equals 2, but the paper that everyone cites that I wrote 5 years ago still has that list of 0, 1, 2, 3. And I'm looking forward to being able to get the new standard out as what people refer to instead of that original paper. And we are possibly within hours of ratifying the new standard so we can publish it. The problem with converting 8.2 up to FP16, you said there were 8 cases that you can't express in FP16. I think FP16, the largest number you could express is 65,504. And you can get a lot bigger than that with an 8.2 posit. But maybe the thing to do is change FP16, because FP16 has the gradual underflow. What if you also add gradual overflow instead of using all those patterns as NaN? What you will land on the largest exponent, and there are 3% of all of the 16-bit floating point representations that are nothing but NaN. So they waste all those bit patterns on meaningless values. The risk, no, it's not risky. ARM has the option of interpreting those as a larger exponent. And I think that solves your problem. You only need 1 NaN value. You don't need 2,048 of them, or 2,047 of them, I guess. 2,046, because there's 2 infinities. Those are the only ones you have to worry about. So that might be an interesting way to go to completely solve your problem of overflow, is fix the floating point.
Yes.
Especially since there's no consistency in following the rules of IEEE as soon as you get below 32-bit. It's anything goes. Some people ignore gradual underflow. Some people enforce it like you're trying to do. And others don't follow the rounding modes. They just clip to 0. Like I think when you turn a 32-bit float into a B float, some people think you just shift it right and chop off the 16 bits. And some people think you have to round it. And I'm not even sure Google has figured out which way it is. But the whole idea of compressing and decompressing into existing floating point hardware, I think, is a really good one. We've used something very similar in our studies at NUS. And I'm looking for any questions to be posted, but once again, we have nothing sent to Pigeonhole. I urge people to use the Pigeonhole tool in order to submit any questions, comments as they hear at any time, and we'll get to them at the end of the talks.
So John, since I'm here,
yes.
Instead of posting the question, I thought maybe I can ask the question itself. So, yes. Instead of Posit 8, have you made any experiments with anything more? Because Posit 8 to FP16, is actually asking for definitely something, big. So did you do anything more than 8 bits on posits? Any experiments?
No,
we've done a lot of experiments with it. Yeah, sorry.
We didn't, because our focus was to improve storage size. Now, if we don't have a power of 2, it's going to be difficult to manage the data layout. So, and we didn't see Posit 12 or the value much discussed. So we didn't consider, but maybe we should.
Okay. Yes, thank you for catching us back up on time. We now are back in sync with the original schedule. Thank you very much, Benoit.
Good, John. I'm surprised you're still holding.
Yes, it's 2:20 in the morning. I'm still awake. We're going to do it.
I didn't see you do this.
Yeah. Well, it's helped that the talks have been so interesting, at least to me.
Oh, definitely.
There are some talks that, really, whoa. But these have been very, very good ones.
That's
so,
right, yeah.
So our next speaker is Mr. Anant Kinal. We'll talk on Posit-enabled RISC-V for accelerating HPC AI workloads. Now this is actually, Ananth and Theo Omtzigt were the first two to recognize that you might be able to make a business out of creating a complete Posit hardware software stack, including all the libraries, the compilers, and everything, and let people really buy a commercial product that would allow you to do experiments, testing which is better, and maybe even have both floats and posits supported on the hardware at the same time. So they've been at this longer than anyone, and in fact, Anand's company, Caligo Tech, was the very first to deliver Posit hardware on an FPGA. He's the co-founder and managing director of Caligo Tech, which is based in Bangalore. And before he founded Caligo Tech, he was the director of engineering at AMD India. He was responsible for server, gaming, CPUs, design verification. Before that, he worked in Intel India's server CPU development team on 6-core and 10-core server CPU designs. And before that, at NextGen and at AMD on AMD K6 and K8 programs. He was the design center head at AMD Singapore. Before that, he worked in Bull, SA, France on multibus 2 IO subsystem connectivity to their mainframe as the chief architect and project leader. He started his career at PSI Data Systems, and this will date him. He was working on DEC PDP-11 compatible CPU designs. Wow, we're old. I remember PDP-11s. Okay, you have it. You have the floor.
Good, John. Thank you so much. So, am I all set? Nicole?
We hear you.
Okay, sure. So, I think, I have, very strong memories of participating in CoNGA 18, and John was mentioning about me and Theo being the very initial people associated with John on essentially, taking his Posit concept into reality. And so I should even go back to 2016 is when actually I met John in the Supercomputing conference in Salt Lake City. And so our journey started from there. So anyway, I'll take you through some of the stuff that we did so far, and then, what our approach is, and then, where we are headed and things like that. And I have my colleague, Giri, who's actually the CTO of the company. So he'll cover some of the slides on the software, experiments that we have done to identify, what kind of applications actually benefit from what Posit N-ES kind of configurations, or for that matter, how Posit 32 is actually sufficient for a lot of computing that we do. In fact, some of it is actually a real customer code for us. So, and he'll discuss more about that. Anyway, so talking about,
You need this first, please.
No, it's not going. So how do I? Nicole? Click the screen.
You can click the screen and then go next.
Okay, yeah, sure. Okay, so I just wanted to give a brief introduction about the company. We are actually a company founded in 2012, and essentially we started the company in the HPC space. For the kind of experience that I had in the CPU side, looking at the kind of problems that were actually happening in the industry that time. Essentially, big data was just kind of starting off. AI was probably, in a very, very nascent stage, and HPC definitely was there, has been there for several decades now. And so one thing that we actually observed was even though there is so much of progress in the hardware side in the CPU in terms of number of cores that are enabled on a CPU and all, we found that software is lagging behind big time. And so we found an opportunity actually in taking up HPC code, essentially parallelize them and optimize them. And so we got onto that stuff. And my colleague Giri, we go back to PSI days. We worked together. And so after that, he has gone into a lot of the firmware and then storage and the software areas. So we thought, we should actually come back, and Giri comes with a very strong storage background in the recent decades. And so I with my compute. So we thought the best area to actually attack is the HPC, because that is where the compute, storage, and the network actually are very important. And so we set ourselves and to essentially looking at how do we parallelize and optimize. And so while we were doing this, in about a year's time, Intel actually in the international supercomputing event in Europe, they announced about 10 worldwide core modernization partners. And I'm happy to say that this announcement by Intel recognizing 10 partners in the world had Caligo Tech also was one of the companies. And this came as a very big surprise for us because we didn't even know that Intel is going to make that announcement. And so it also put a lot of responsibility on us because we needed to actually cover the other areas of code modernization as being a partner for Intel. And what I can say is, we did several, HPC-centric engagements with Intel, including, trainings and code modernization for customers, and some of the stuff for Intel itself. And so that work we essentially, were able to do, and so that set off us really into the HPC space. And since we were at it, the AI also was something that was essentially gaining importance, and so we worked very strongly with some of the AI leaders in the country, and so we were actually recognized as one of 4 AI partners for Intel India, and so we were selected to build the framework for AI. And so on the big data side, Giri actually has architected a intelligent data analytics platform, and I think so we'll probably have another opportunity to go deeper into the stuff that we have done in the AI and then big data space. But at a high level, this also gave us an opportunity for us to be in the Intel's ISV partner ecosystem, and then so we are one of the Intel AI builders. We appear on an Intel website showcasing our side app product. And the focus of this presentation actually is the one on the top left corner, which is essentially the silicon and systems. And while we were on the journey for performance, we were looking at what fundamentally can be different for amplifying the kind of performance or the power that actually gets consumed at a HPC level or a supercomputing level. And that is when I just was at SC16, and then there was a side presentation by John, and then I happened to actually meet John there. And I still remember the day, where we met in some corner, and then we talked about, what does he want? And, with my experience in next gen and AMD and all, we thought, we should actually group together. And then so we started interacting very closely during 2017 timeframe. And 4 of us, John, myself, Serlane, and Theo, we met very often. And then so during this period, we actually conceptualized hardware for implementing John's Posit number system. And so we essentially just built a coprocessor, and we found a way actually, putting this coprocessor in an FPGA form in a SoC FPGA environment, where essentially you have a operating system and then an ARM-based SoC FPGA environment actually rendered, shipping the operands to the Posit numeric unit, which is our coprocessor, and then sending out the opcode bus on the opcode, and then getting the results back from the FPGA. So that is the kind of thing that we actually put together, and then we were able to demonstrate this standalone processor at SC18, and so this was about 4 years back, and we demonstrated this in CoNGA on one of the side events there. Right? So this is with this we realized that we have a basic coprocessor which can actually do Posit-based computation, and since I come from Intel days, and where Intel actually started out with a processor plus a coprocessor, and how you do two things separately, and then how actually process technology allowed you to essentially combine the two things and build a CPU core. So exactly that's a path that we want to take. And so since we had already built a coprocessor, our next lookout for was actually what is a core that we can integrate this with. And so it was probably one of the very easy decisions for us at that point of time, considering we went with RISC-V, and the decision was very easy because of the simpleness of RISC-V. And on one side, CISC versus RISC, that fighting was, fight is on from several decades now, and RISC-V is definitely giving a very good competition. And so for a simple processor like RISC-V, we thought we should definitely have a simple coprocessor like a Posit-enabled our PNU. And what John also mentioned was that he actually was asked by the RISC designers to actually come up with something which will take away a lot of baggage from the real number computation which existed in the floating point number system. So that's where we essentially got the two together, and I'll just so going back to what I just said, SC17 is where we started with the emerging technologies track, presenting a paper there, and then essentially demonstrating the Posit numeric unit standalone in the SC Asia event, and then so the RISC-V integration that we did was with a open source code from a company called BlueSpec, and so we leveraged their Flute core and integrated our PNU with their Flute core, and we were able to actually demonstrate booting of Linux and running of applications actually just about 4 months after we had this collaboration with BlueSpec. So side by side, we also had to do compiler modifications, because when you're talking about modifications as fundamental as a number system change, that definitely you have to supplement that with the compiler support. And so we did a lot of work on the enhancements of the C++ compiler to be able to actually support posits. And for the fact that we just wanted to piggyback on the FND extensions of RISC-V, we decided to go with two posit configurations. One is the 32,2 in place of float, and 64,3 in place of double. So this approach actually was something important because we didn't want to do a whole lot of compiler design from scratch, and we definitely wanted to leverage as much ecosystem that existed in the RISC-V community at that point of time. So that was the demonstration that we did in Switzerland RISC-V workshop, and so essentially, since we are building a platform, we also wanted to actually create something which can compare a floating point unit with our Posit numeric unit for an apples-to-apples comparison of the results from the same platform. So we essentially, alongside of integrating the Posit numeric unit, we also made sure that we continue to keep the floating point unit, and with a soft selection of a bit in the CSR, we essentially select either between we select either a floating point or a Posit numeric unit. And so I covered that by the FND instructions of the RISC-V. We essentially piggyback on the 32,2 single precision, double precision, actually piggyback using the 32,2 and 64,3 Posit configurations. So for the fact that we have done this, N-ES 2 configurations that can be supported, we also can actually have different N-ES pair. It need not be 32,2 and 64,3. It can be anything and anything. So that is because the compiler modification that we have done is flexible enough to give us the compiler for any N-ES twin combinations of that, piggybacking on the FND instructions. And we also wanted to actually the hardware configuration actually is again design is modular, and so we will be able to essentially get that into the hardware quickly alongside of the software as compiler modifications. So so we wanted to essentially create this platform to be able to do experiments on large number of HPC applications, and then the AI framework and things like that existed at the time. And so once what we also wanted to do was, once we have done the proof using the FPGAs, we wanted to actually build a multi-core system on chip to power an accelerator board, and build a many-core system on chip to power self-booting motherboard. So for people who have actually kept track of how Intel did, for example, the Xeon Phi processor, we have followed a very similar approach, essentially taking an accelerator board approach initially, so that you view the capabilities of what you want to add new on a standard server, and then essentially bringing this whole technology into a self-booting motherboard kind of a concept. So that's exactly where we want to go. But today we are actually at the place where we want building the multi-core system on chip to power an accelerator board. Diagrammatically, this is what we have done, and so this is our approach. And so, as I mentioned, we built the Posit numeric unit, and then we integrated that with RISC-V. And then so we actually call this as CRISP core, which is Caligos CRISP-5 with posits. So we created this, and then this is what was demonstrated in RISC-V in Switzerland. And so this is where we are heading, and we are well funded now at this point of time to essentially build the first version of the chip. And if all goes as planned, we want to actually demonstrate the first chip actually in the November 22, the SE in the USA later this year, towards the end of this year. So all that actually, pure hardware work was not sufficient. So significant amount of work done on C++ compilers is what has actually brought us to this level. So we didn't have to do any modifications in the compiler level, or sorry, the operating system level. So we could just take any Linux OS running on a RISC-V and then essentially get that to run with our CRISP core. So that advantage is there for us. So as I mentioned, our system on chip actually will have a multi-core version of the chip, and so depending on how our die size, there are some constraints in which we are actually currently working. So depending on how many cores we can actually accommodate, we will try to see if we can squeeze up to 64 cores, and then so build the PCB which will take our system on chip and then with the other components around it, and we essentially build an accelerator card of this nature, which will go into any standard server. And for the fact that we'll have a lot of the software components running on this, we'll actually be able to change this and change the functionality of this accelerator depending on what software runs on this. And so it will be essentially a software-defined accelerator, and we are targeting the HPC and AI workloads. And essentially, in terms of customers, for the fact that John has done some very disruptive invention, I think this is what should really reach the supercomputers in the world, and a lot of the HPC customers should actually be benefiting from the advantages of Posit. And so that's what we will do is as we get closer to the implementation of the chip and powering on the chip and things like that, by that time we would have actually identified 3 to 5 HPC verticals which can benefit big time from the Posits, and then essentially enable those configuration-based products so that the HPC application sees a significant performance advantage. And so we are also looking at some of the AI stuff, and I'll talk about how we will approach the AI path. And so the next step, like I talked about, essentially this is in a couple of years down the road, we should actually be getting to many core with about 1024 cores and self-booting motherboard. And so we'll target high volume and low selling, average selling price kind of opportunity for that. So in a nutshell, this is exactly what will be, once we have our, we call our silicon actually called, it's a CoNGA, which is actually a technology with Unum for next generation arithmetic. So I have essentially flicked part of John's acronym for naming our chip. So that is the chip that we will have as the first version. And then, so we will build an accelerator as I shown here. And the OEM server, it could be any CPU, it could be x86 CPU or an ARM CPU or a PowerPC CPU. So we'll just take that, and then our accelerator board should actually plug into any of these and essentially speed up the HPC workloads or AI big data workloads, and essentially Posit enabled environment is what we will have with that. So our chip, what we are targeting is a 64-bit RISC-V processor core. So in the final implementation, we will not have FPU. I'll talk about another platform that we have which supports FPU, but so our chip will not have FPU. It will be co-processor supporting 64,3 and 32,2 posits, like the way I mentioned, directly leveraging the FND instructions of RISC-V. And so it will be multiple cores and then multi-level caches and all the other controllers that are actually necessary for a system on chip. So that's what is the planned chip. And so at this point, again, I'll hand over to Giri, my colleague who's the CTO of the company, and he'll run through some of the experiments that we have done on the CRISP core and then share some results.
Thank you, Anand. Hello, everyone. See, what we are going to really do is, I'm going to show you the experiments, whatever we have done, and the results, associated results, whatever we have received on our platform. That is what I'm going to really do it. So to start with, what we have really done is, we have taken the Rum's equation. If you see Rum's equation, on IBM 370, we were able to get the precision, which is mentioned on the above, so that is what we were able to really get it. But if you want to really run Rum's equation using IEEE 754, unfortunately, IEEE 754 will not give you the right result unless you modify the equation itself. That is when you will be able to achieve what IBM 370 has done it without modifying the equation itself. So what we have really done is, we have taken this classic problem and we were able to run it as is condition on our CRISP code, and we were able to achieve get the right results using 32,2. If you compare these two results, if you see that what we were able to really achieve is up to 8-digit precision, we were able to get it on our 32,2 as compared to IBM 370 itself. That is what we were able to really achieve on our CRISP code. And moving on to the next experiment, what we have really done is, majority of the people, they were asking, is it possible for us to port any of the BLAST functions onto, Posit itself. So initially we were looking at OpenBLAST, but unfortunately OpenBLAST has a lot of Fortran code as well as assembly code. So we were not able to really do that. So what we have really done is, we have taken the alternate approach. The C BLAST is again C code with the BLAST functionality. That is what we have really done, taken that, and we were able to convert that into Posit. So to test that, our C BLAST code itself, what we have really done is, there is something called REK. So which is going to take a sparse matrix of 5000 by 500 matrix, and then it is going to really do the multiplication, and then at the dense matrix multiplication, it is going to really do that. So if you see on the above, which is running on the x86 using double, the LS error, you were able to really get it on a sparse REK. On a dense REK, if you see that LS error is 187 dot something else, this is what you are able to really get it. So what we were able to really do is, we were able to run that on our CRISP platform, 32,2. So the LS error for sparse REK is exactly matching the value we were able to get it on x86 double. Now we are not running a double, rather we are using 32,2. But when you are doing it on a dense matrix, this 5000 by 500, if you see that the LS error has come down, 187 versus 184. That is what we were able to achieve using, our version of Posit. That is what we have done it. And then the next one is, what we have really done is, we wanted to experiment with all other, different applications. So we have taken Black-Scholes, and we were able to run Black-Scholes on x86 double. And these are all the strike price, asset price, and then call value, put value. If you see that all the values are mentioned over there. The same thing when we were able to run it on CRISP 32,2, we were able to get this, which is almost, it is matching the value what we were able to get it on x86 double. Now moving on to Brownian motion, that is one more experiment that we wanted to really do that, how the Brownian moment, is going to work on the posits. So what we were able to really do that, if you see here, what I have captured is motion 1D data on x86 64. That is what we have done that. And now we are going to use 48,3. That is what we have done it. If you see that 48,3, it exactly matches with 64-bit precision, whatever we were able to get it on x86 itself. That means, we don't have to really use 64 bits. Rather, we can use only 48 bits for us to really get the value, desired value, whatever we are looking at. That means, we are going to get 25% extra benefit over whatever x86 64 is currently providing. Moving on to the next one. This is for a customer application that we have really taken. One of our prestigious customer, he has given some code, C++ code. So we were thinking, how is it going to really work on a Posit itself? So what we have really done is, we have taken the code, we have ran it on x86 FPU double. So if you see on the left-hand side, excuse me, I'm sorry. On the left-hand side, whatever data that we were getting, that is on the FPU double precision. On the right hand side, this is PNU 32,2. So if you see that majority of the value, whatever we have received on x86 double precision is matching with the PNU 32,2. So this is in short, in a nutshell, that with whatever compiler modification that we have done, we were able to achieve it on our hardware platform itself.
So I mentioned, I would talk about a platform a little later, and so this is the time for that. And so, so this is the FPGA-based platform onto which we have the CRISP core that we have that I mentioned earlier. Just a minute, please. Okay, sorry about that. The battery went low and we had to connect the power source. Okay, so this is the FPGA board, and on the left side you have a high-level architectural understanding of what we have done. So as I mentioned, we have both a FPU and a PNU as a part of our design, and then there is a switch that actually selects whether we run with FPU or with PNU. And on the server or any x86 platform, or for that matter any compute platform, we have a cross compiler which actually can generate the FPU enabled code or PNU enabled code. And so essentially, depending on what we want to select out of these two, we would set that switch and then enable that executable to run on this. And then so just by not doing that turning on of FPU, by turning on PNU on the same exact hardware with the different executable, you'll be able to run the same exact application on the same hardware. So the results are actually can be compared on an apples to apples comparison, because it is running exactly on the same hardware. So you don't have any other parameters like access to the memory, whether it's faster or slower, in two different environments. So all such problem is not there. And so we are actually we have created a platform which really gives an apples to apples comparison between a PNU based executable and a FP based executable, and when we run that. So this is something that we use for example, whatever Giri actually discussed the results, most of all that experiment actually has been done on this platform. And so we are making this available to customers who want to do Posit based experiments. And so at a high level, this is what is the hardware configuration of the board, and then what it supports, and essentially whatever we discussed so far is what essentially is there captured on this. And then what software and the kind of little or no modification that is required to source code. That's exactly what has made things so easy for us. And Giri talked about C-BLAST based application porting, and I can say that just in about a day's well within a day we were able to just simply compile all the stuff that there in the C-BLAST into a Posit enabled C-BLAST, and then we are able to take this same the applications which are some suite of test cases that run on C-BLAST, and so we are able to run all that stuff seamlessly, and essentially we are able to Posit enable or do computations in the Posit world without any very effortlessly. So that is the kind of advantage that we have with this kind of a platform. So what we want to urge the audience is, if anybody has any requirements of seeing whether their application actually can benefit from Posits. If it can benefit, then what Posit configuration will be the most suitable for their application. Such kind of experiments can be done on this. So we can offer this the entire hardware and software infrastructure, and we can even give additional help and things like that to essentially get to all those experiments. And in case customer actually is looking for if say that there's a huge application base that a customer is currently running on, say, in a float environment, we can essentially take that and then take it through the process that we've done for the example application that we mentioned, and we can come back with code which is Posit enabled, and also for the fact that we are very strong in code optimization and parallelization, we'll be able to apply that also to the final code, and because of that, you can imagine the kind of performance advantages that is possible to actually bring into applications. So we can essentially even build a silicon board and compiler for customer requirements, depending on what Posit configuration suits them best. And as I mentioned already, that our hardware actually is versatile enough, and we will be able to do modifications to the FPGA very quickly, and then also do the modifications to the compiler. So we will be able to come up with the most optimal N-ES configurations that will be suitable for a specific application. So the other model is essentially where the customer buys the platform from us, and then we will support them to actually do all these experiments in-house at their premises. So this is the kind of engagement models that are possible today. And as we get to our multi-core version of the chip, and we'll also have an intermediate version in the form of FPGAs. And so what we want to do is, we also want to offer this to the customers. So it's going to be a multi-core Linux with an accelerator support. And those of you who actually heard Theo in the morning, so essentially accelerator support for different use cases, different Posit configurations, all that actually is possible. And so we will be able to supply that also. And of course, as we get to the real silicon, sometime in the next year, we'll definitely be selling the accelerator board for different applications, and applications which benefit from Posit. So definitely there's a lot to be actually still experimented with. And this is, I think, what John also mentions in many of his presentations, that the advantages of Posits, I think nobody has really even understood to what depth it can go. Definitely, footprint in terms of program or data storage, or for that matter, the amount of storage that is required in the form of hard disk or NVMe, or essentially storage outside the system, and of course the network bandwidth that is required to efficiently run a HPC application. All that actually gets significantly advantaged by going in for Posit-based code base. So definitely we are very eager to get to the multi-core version of the chip first, and then as quickly get to the HPC configurations in clustered modes, essentially enabling in a much bigger way the Posit enabled computing across the different modes. And so this should actually enable, for the fact that the fundamental change that's going to happen at the bottommost level, which is at the single core level, what changes that we are doing, that actually should be amplifying in a very, very big way as we get to the larger cluster configurations and more number of CPUs and things like that. So just to conclude, we are essentially on the journey to actually make Posits as one of the compute standards, and it could even be for specific applications, the making of the hardware and software, the platform specifically for specific applications. So we will have more of that, and we'll probably share that as we start making conclusions about what is the best for what. So we'll be essentially targeting platforms for specific applications. And one thing that we have done is we have taken a general purpose computing approach. This essentially opens up a lot of Posit enabled computing to a large number of applications. And as I said, C++ is essentially across everywhere. Even if I talk about, say, TensorFlow, today I can actually get to a C++ code and then essentially come back to this path of taking it through our C++ compilation and Posit enabled say AI application. So that's what I think our approach, we are very confident that it'll give lot of advantages because of its general nature. And so what we have done actually is a combination of two disruptive technologies, a simple processor like RISC-V and a simple coprocessor like our Posit numeric unit. And so, with this, I know exascale is already in the horizon, and definitely, once we have this, in the form of silicon and then accelerator board and things like that, I'm pretty sure this will add a lot to how exascale actually can be configured and essentially benefiting from posits. So this is what we have done, and so we also look for opportunities for essentially designing system on chips for customer specific configurations, and we can actually proceed it with the experiments to identify what best N(ES) works the best for the customer application. And so that's what we are actually looking for in terms of business. And so we definitely will have accelerator for now, and then we'll have cell booting motherboard to follow. So that's essentially what I wanted to communicate today. So here are contact details, and in case you have more questions, you can also visit our website. Some amount of information is there related to CRISP and things like that. And so definitely you can ask more questions if you have through either email or I'm willing to take some questions now.
Thank you, Anant. We do have some questions. And one of them is from Hockey Rare. He says, did you also try float instead of double when you were comparing against 64-bit floats? Posit of any size doing as well as double doesn't tell us anything if float also does equally well. So you have to show that float fails and posits at 32-bit float fails, but if 32-bit posit succeeds, then it's safe to go to the lower bandwidth requirement.
So, and I'll also take Giri's help in answering some of these questions. So one thing what I can say is the very first example, the Rum's equation, essentially is a very good example of Posit 32 actually matching the results of double. And so that is something which says very clearly that, and the Rump equation experiments that were done, if you actually see the paper, the single position actually gave completely different answer. It didn't even, I think it even had a negative sign. So that is what is float 32 for Rump's equation. Okay.
I want to take Rump's equation offline with you. I don't want to get into that right now. It's a deeper problem. But in general, it's very powerful to show that Posit 32,2 succeeds, float standard 32 does not. And here is the gold standard, the 64-bit value, and why you trust it. I guess he's just giving you some coaching as to how to present this in a very clear and understandable way.
Perfect, John. In fact, I can tell you, the customer experiment, whatever we have really done, there actually we have done float 32 as well as double. Compared that with 32,2, and 32,2 definitely exceeds the float 32 whatever work that we have done. So it is getting as close as actually double value. That is what actually I have shown in you there.
Mm-hmm. Yeah, so I'm very interested in collecting examples where you do need double precision, and I haven't. I certainly found things where 32-bit posits might not be quite enough, but if you add to that the quire, then I haven't found anything you can't do with the 32-bit posit supplemented with the quire. We also have a question from Raul Murillo. He says, you mentioned your course supports both FPU and PNU. Do you have any comparison of overhead in terms of area and performance of the PNU over the FPU? Also, is the FPU compliant with IEEE 754?
Yes, so I'll answer the second question first. Yes, it is. The FPU is IEEE 754 compliant. And in terms of area, what we have seen actually is the Posit-based hardware actually takes about 15% more than the IEEE floating point. But we know that we have a lot of optimizations that can be done. And again, the goal here today for us actually is functionality, and that's what we have achieved when implementing the Calico Posit development platform. So, but the silicon that we are doing, definitely that will be a different answer. So we can probably share that information in the ISC sometime in June, July timeframe.
Yeah, 15% is not bad at all. Excellent. I think they're very, very comparable, which is what we always hoped.
Right.
And thus concludes the first day of CoNGA 2022. Want to thank all the speakers. We're right on time. It is exactly 6 p.m. in Singapore. I do want to suggest that you tell your colleagues in this area to think about CoNGA 2023. I noticed that there's about a new Posit paper published every 2 days. That's an awful lot of technical papers. If you can imagine that we would get 150 submissions, it could be quite a conference. We could do a whole week. So goodbye for now. I will see you at day 3 of CoNGA.
Thanks, John.
Thank you.
Get some sleep now. Good night.
I'll get some sleep now. Thank you.
Bye then. Yeah. Bye.
Bye.